There you go. You're up on the screen.
Okay.
Yeah. So you can say hello.
Hello.
Marvelous. And I love the boat.
Yeah, it's to remind people why they work.
All right. Good morning, folks. My name's Will Pettit. I'm the Executive Director of Geothermal Rising. Most of you know who I am or have seen me. I just wanted to say a few words before handing over to our fantastic chairs, Lou and Jeff, and who can give themselves a bit more of an introduction, their bios. So we are running today's workshop as a webinar so that folks from outside of this room can join in. So we will have both in-person and virtual attendees here, and we'll be managing it to get everybody talking as best we can with questions and Q&A and that kind of thing. So the attendees that are in virtual world can see basically what we have on the screen here. They can see the room, they can see anybody speaking at the podium. The way that it works is effectively just like a Zoom meeting. So I just wanted to kind of introduce that to you a little bit so that you can get a feel for how it all works. So basically, we have, just like in an ordinary Zoom meeting, we have a video on the presenter during a presentation up at the podium. A presenter, if you are a presenter, you come up to the podium and we can help at any time, but you just come up to the podium with your presentation, maybe preloaded or not, and screen share from this podium PC. So just like in Zoom meeting, we are running everything off screen sharing. So everything's live, flowing out into the outside world. As long as the internet stays with us, it will all work fine. So we just screen share from the podium. That means that the folks outside of the room are seeing everything. We're also recording it so that it's available after the event. And actually what's displayed on the screen here is then what is displayed by what is seen by folks outside. This is actually the Zoom coming back into the room. And we can control a little bit of that from within here and using our Zoom functions and all that kind of stuff. It's amazing when you get into this, how many things you learn about Zoom. And then for folks who are presenting virtually, it's exactly the same. They just are treating it like a Zoom meeting. They're coming in, talking just like Steve is here on the screen, and then are able to share their screen when they want to present their slides and do it completely from their own computer. So that's the mechanics of it all. So, and I think that's enough from me. So I'm just going to hand it straight over to Lou and Jeff.
Thank you. Thank you. Thank you. Can you hear me? Yeah. Welcome, all of you. I'm glad you all could be here. My name is Louis Capiano. I'm petroleum engineer, but I've been in geothermal for a few eons now, since 1974. So I've been doing a lot of geothermal drilling. So, you know, people ask me as a drilling engineer, you know, what's the most important aspect of drilling a geothermal well? And the most important aspect is a good cement job. And that's why we're all here. We need to get a good cement job or our wells won't last. And so to give you a little background, I've been a drilling engineer in geothermal, like I said, since '74, working in a lot of places in the world. So I've seen a lot of things and we have a lot of experience. I'll turn it over to here, Jeff, in a minute. He's on my counterpart from the SPE. This is the second workshop that was put on jointly by SPE and the geothermal industry. First one was corrosion, which was very successful. And we hope to keep going and keep having a series of joint workshops. So keep in mind what you would like to see maybe on the next workshop. And I can see cementing being another one after this one, because we can't cover everything in this one workshop. A few points of information I'm going to propose to you right now is that there's been a few cancellations, and it's been requested that we try to compress the program so that we can do the final panel on Friday night, so some of the people can leave on Saturday morning. We will still have breakfast and we'll still have a meeting here, but it may not be as important if we can do the final panel Friday night at the end. A lot of us were at the geothermal conference and we've been here since last Saturday. So we're getting kind of tired and we're ready to move on, but we want to be here for everybody. And I'd like to make this, I mean, we're a small group. We ought to make it proactive. So please, let's hear your questions. Let's talk, let's discuss. We've got enough breaks in time that we can get around and talk and between breaks and everything else. So I'm gonna turn it over to Jeff now. By the way, the restrooms are out the door, down the hall to the right. If anybody needs to go. And so we're here. Jeff, it's up to you.
Well, good morning, everybody. How are you doing? Yeah, it's great to finally be here in person. This thing's been being planned since 2018. And so, well, here we are. So we want to thank everybody who's able to be here in person for making your way here and attending. Want to thank our speakers and our presenters for the efforts that went into putting everything together. Our session chairs, thank you very much for all your hard work in getting your sessions ready. And then to our organizers at the GRC and the SPE, lots of long hours went into finding a way to make this work, and having to reschedule this meeting a few times, run a virtual one, and now we're running this one. And then the decision kind of at the 11th hour to add the virtual component into this and find a way to make that work. So thank you to everybody there. As Lou was saying, we want this to be a casual event. We're a pretty small group that's here, and want everybody to take the opportunity to meet and share ideas and challenge each other to think about how we can use technology to achieve what our objectives are here, and how can we change the status quo and go back and maybe dust off some old ideas that didn't work in the past, but maybe work now as things have changed, or think of different ways that we can solve these problems. As you all know, there's a world that's got a hungry demand for energy out there, and we're certainly seeing some ripples show up, maybe bigger than ripples show up in what the energy market's doing right now. And all aspects of energy are going to be important for us to be successful as a society.
Since we're such a small group, we thought it would be interesting, Jeff and I, maybe everybody stood up and just introduce yourself and who you work for, just quick, so we know everybody, and so people can connect with people that they may want to talk to later on. We'll start Ricker, you started off over there and then we'll go right around the room.
I'm Bill Rickard and the Geothermal Resource Group. And it's got 3 years on me in experience. I didn't start until 77 at the geysers and I couldn't agree. Thank you. I didn't start until 77 at the geysers and I couldn't agree with them more that cementing is the most important part of a geothermal well completion. My name is Mark Chastain. I work for Cal Energy. I'm the drawing superintendent for them. I don't use this. My name is Mark. I work for Cal Energy. I'm the drawing superintendent for Cal Energy.
Billy Thomas, also resource and drilling at Cal Energy. I'm senior geoscientist now, but got a small department there, just a few people, and work closely with Mark and John Trujillo.
Good morning, everyone. Curious Agapio with Halliburton Cementing.
Rafael Hernandez, pedal casing equipment with Megafec.
Good morning, Patrick Gerard. I'm the Schlumberger U.S. sales manager for cement and mud.
I'm Jeff Landry. I'm the cementing tech manager for Schlumberger North America.
Mark Otter, lead the well engineering team at Ever Technologies.
My name is Larry Glaser. I'm with American Gilsonite Company. Gilsonite's an additive commonly used both in drilling fluids and cementing.
Oklahoma State University.
And Will Pettit, Geothermal Rising. And please do remember that the folks online can only hear you if you speak into a microphone. So please do speak into a microphone when you can.
Hi, I'm Bob Pilko with Blade Energy Partners. We're complex and critical well designers.
Good morning. My name is Sam Abraham, and I work for Geothermal Resource Group as a drilling engineer, project manager, looking after projects worldwide. Thank you.
Good morning. Mark Brennan, Resource Cementing, business development manager, and I'm in Northern California.
Good morning, Hamid Najafi with Resource Cementing.
My name is Catalin Teodorio. I'm with the University of Oklahoma, and we do a lot of research in well integrity, oil and gas, and geothermal.
I'm Dalton Hoscroft, Cancor Smetters. We're from Northern BC.
John McCormick. I'm with a software company. We do some cementing software. It's Pegasus Vertex. So we're here to learn a few things.
Arash Dahi from Penn State University.
Reinaldo Maldonado from Impact. We are product manufacturer.
I'm Arpita Batija from Aramco Research Center. I'm in the drilling technology team in the cementing group.
I'm Courtney Luxford. I'm with the Nevada Division of Minerals. I'm the Fluids Mineral Program Manager and in charge of all the permitting for oil, gas, geothermal, and dissolved minerals in the state.
Hi, good morning. Jose Iguaz with Baker Hughes, and I'm with the Global Geothermal team of Baker Hughes.
Ernesto Rivas with Geothermal Resource Group.
Good morning. My name is Dirk Valster. I'm with Schlumberger, and I am the well integrity domain champion for wireline. So I look at all the cement logs you run after you put the cement in the well.
Good morning. I'm Nicolas Droger with Schlumberger as well, cementing sustaining leader based in Sugarland.
Good morning. I'm Gabriel Rossi with Valorec, and we do tubing and casing.
Morning, Matt Kellum. I'm the cementing R&D team lead based out of Tomball, Texas for Baker Hughes.
Good morning, Daniel Boer with Boer Consulting, independent consultant working on cementing oil and gas and geothermal wells.
And good morning, Sam Atalay, Geothermal Resource Group.
I'm Susan Petty. I'm the Chief Technology Officer for Circ Energy, and I'm also the President and CTO of Ultrarock Energy. And I've been in the geothermal business now for 43 years. I'm a consumer of geothermal cement and high temperature well completions. Thanks.
Well, thank you. And I realized that I didn't introduce myself. I'm Jeff Spence. I'm the Vice President of Operations and Innovation for Sanjel Energy Services.
We're going to start off with the first panel here pretty soon, and Jeff and I will moderate, but we're not going to be on the panel ourselves. So yeah, well, we're tired today just to prove that drilling engineers don't always wear jeans and boots, you know. So we sometimes dress up, although it probably hadn't had this tie on since before COVID, you know. So with that, I'd like to introduce the panel. The two from the geothermal side are, you can see him up there in front of his boat there. One is Steve Pye. Steve Pye has been in geothermal for many years. He's a hell of a lot older than I am, so we let him. We like to have him on the panel. He's got a lot of experience. The other one, Daniel, you're on the first panel. Daniel Borg is on the first panel, so you might want to come up here, Daniel, and you get the rest of them.
Yeah, and our third panel member is Jeff Landry from Schlumberger. So Daniel and Jeff, if you want to come join me on the stage, we'll kick this off, and Steve will be hanging out by his boat. Yeah. Well, thanks for joining me here, guys. What I thought I'd start the conversations off with today is well integrity. It's we talk about getting a good cement job, but why is it that we're after a good cement job? And to me, it comes down to well integrity. And I thought that we'd maybe just go across the panel and say, how do you see well integrity, the solutions to well integrity, and how does it factor into geothermal wells and making them a long-term success? So Steve, maybe we'll start with you on the screen there.
Okay. We submit these wells, the casing in place in these wells, and that casing and cement combination have to last 30 years for the economic life of the well. And we talk a lot about what we're doing to improve success. And I think we need to encourage people to talk about the failures, because when we have a failure of the cement, not just a slow corrosion of the cement, but when we have a total failure of getting the cement in place properly, we end up with a well that's damaged, sometimes beyond repair. And if we don't talk about why we failed, we won't necessarily figure out how not to fail. And so you may do the same thing in cementing your casing in place 5 times, and 1 time out of that 5, it fails. And so if we don't talk about the failures as well as the successes, I think we're missing an opportunity to do a better job.
Yeah, it's so true. And that's what we're here to work together as a group on, is learn from challenges. Those usually lead to technology initiatives, and to find ways that we can implement that across the spectrum to be ultimately more successful. So Jeff, do you want to share your thoughts?
Sure. I mean, I think this thing on. Hello. All right. So I think Steve, really hit the nail on the head about failures, because that's where we actually learn and how to innovate towards solutions to mitigate the future. A geothermal well is arguably more complex than a lot of the counterparts in the oil and gas industry, right? You usually have the formations that you're trying to target can lead to problems in placement, right? Placing of the cement job is number 1. Getting it around pipe is critical. Doing the basics are critical, but sometimes in a geothermal environment, the basics are actually quite challenging. And then moving forward into just the cyclic loading that the well will see in the life of the well that it has to have. All these components with the temperature changes and the pressure changes puts the seaman under a lot of stress, right? And how do we mitigate those failures, not just in the short term, but also in the life of the well, and make sure the economics play out the way that we all planned in the beginning, I think are where cement really comes into play, just from a high level, right? So learning why, communicating why we fell, writing case studies, why we fell, making sure we get that data through SBE and other organizations out there so we can all learn and grow, I think is a key initiative. And I'm sure today we're going to talk a lot about the different challenges, but from a very high level, I really see the failure communication, as Steve said, is very critical. And getting cement placed around pipe. So it's good to see some casing hardware and other things, and making sure that we have that key aspect done. The top of cement and cement around pipe is the first step, and all the technology and bells and whistles you want to put in the cement really don't matter unless you achieve that goal. That's kind of.
Daniel, do you want to share your thoughts?
Yeah, I'm trying to distill 7 or 5 day cementing course in about 5 minutes, but I'll do that. I just think in terms of dollars, what's the cost of failure? When you have, and we can come up with the greatest technology, but if no one's going to implement it because it's quote too expensive, then we're wasting our time. So we need to start with what's the cost of failure. And the cost of failure of a geothermal well is, I mean, if 20% of the cars you drove off a lot failed on you, you wouldn't go back to that car lot, because, you can't afford to buy every out of 10 cars, 2 cars just crap out on you. So the cost of failure is a big one. It's either workover, which is very expensive, or a total loss of the well. And then I go through my first presentation where I'm going to talk about the various aspects of material, looking at getting the right material. And there's a lot of scientists here that focus on that. And that's important. We need good materials. But there's also the critical step of taking those materials from the laboratory to actual field operations and working with a guy like Lou or Bill and getting it implemented actually in field operations. That's a critical step that we need to take a lot of time and focus on, make sure we don't just throw a good idea over the wall and then hope operations can figure out how to run it. And then also, yeah, operations is a big one. We do have a lot of good materials. We do have a lot of good techniques. We just need to make sure that we're effectively communicating with the people that make decisions on the importance of using best practices. So I'll harp on that, and when I get to talk about my the main issue. And then a phrase I like to use that geothermal is like oil and gas, only it's different. There's a lot of similarities, but there's a lot of differences, and you need to really be clear on those things. We invite a lot of people from the oil and gas industry come in with their solutions, and they've got the latest technology, but they also need to understand there's a lot of differences, and they need to take that in consideration. The most critical part of a cement job in an oil and gas well is cross production zone. The most critical part of a geothermal well is the cement at surface and getting cement to surface. So it's similar but different, and we need to be able to distinguish between those things. And I guess I'll get a chance to opine on several of these things in detail when I get into my talk later.
All right, thanks, guys. It's interesting to see a couple of different segments of the energy sector come together and hear the different thoughts and different concerns that come from it, whether it's geothermal or oil and gas. And so what I'd like to hear from the panel next, or the question I'd ask them is, what do you see from a high temperature well perspective, what do you see as the biggest opportunities that are out there that are waiting to be grasped? Daniel, maybe we'll start with you on that.
Opportunities in terms of what?
It could be a technology that just hasn't quite come to maturity yet, or whether it's a way to achieve a certain energy output, or it could be something like thermal conductivity of the cement, or how do you stop vent flows from happening? Like, what do we need to take high temperature cementing to that next level to solve that kind of imminent challenge, or provide a technology that's going to help, whether it's geothermal or high temperature oil and gas wells, be more successful in the current environment?
So I'll try and limit it. I can think of multiple things. Mechanical properties of cement's critical. I'm talking and working with several people. We not only need cement to be hard, actually, we don't really need cement to be hard. We need it to be durable, and it needs to withstand the cyclic loads that are going to go. And therefore, we need good programs to actually model what's going to happen. And there's some good technologies coming, and there's some good technologies already available with some of the major service companies and some independents that I'm aware of. We need new materials. We're looking at wells supercritical and higher, and Portland cement. I'm working on a project. We're right on the edge. And how do you get so there's opportunities to move away from ordinary Portland cement. So that's a great area of opportunity. There's the, so I just worked on a project where we're trying to, oh, by the way, we need to retard cement for a placement temperature of 540 degrees Fahrenheit. I'd never done that before. And guess what? We actually did it. So I was kind of proud of myself, or actually proud of the guy who did the work. But as we start talking about supercritical and very high temperatures, it's normally in a geothermal well, we can cool it down quite a bit. And so we don't really face a lot of challenge in getting it in place. But there's going to be more and more situations where actually the fluid temperature is going to be extremely high. Not only how do we get it to retard that, but do we even have test equipment? I would say 99% of the cement labs in the world can't test above 400 degrees F, 200 C. And I happen to be working with someone who happened to have equipment that went to 600, but that's a rarity. So as we move up in these higher temperature ranges, we'll need to understand that. And then what are the fluid properties at 500 degrees? I mean, we look at it at 80 and 100, you know, at room temperatures, and we extrapolate to those higher temperatures. Well, that's nice to think that's true, but it's probably not the truth. So we need testing. We need new replacements for Portland cement, and several people will opine on that, including myself. We need durable cement materials that remain intact, that provide casing support. And we still need some help in the fundamentals of overcoming the problems of lost circulation. And several of us will talk about that, because it's critical that we get cement to surface, not just hope it gets there, but it has to get there or the cost is going to be excessive. So that's my short version.
And thanks, Jeff.
I mean, what else is there to say? I mean, no. So like Daniel said, right? I mean, when you're looking at what's on the horizon, or what are some of the possibilities, right? You got the material part of it is a key component, right? We've been using Portland cement, honestly, because it's been used, and it was used in other industries, but is that the right place for geothermal wells? They're similar, but they're different, right? As like Daniel said, and it's Portland cement where we really need to be. If you look at the byproducts at different temperatures that you're at, right, it doesn't really play friendly with some of the temperatures, most of the temperatures that you're going to be at. It's probably not an ideal material. So there's a lot there, right, on non-Portland. I hate the word used, cementitious, because it's derived from Portland cement, but durable materials that can be placed in the way that we need it, and also provide the isolation and the ductility and the cyclic loading, I think, is a key part. And it's the mechanical properties for a geothermal well could include a lot more than what an oil and gas. It's more than Young's modulus. It's more than Pascal's ratio. You're looking at thermal expansion. You're looking at thermal conductivity and resistance. You got a lot of things else to consider on top of maybe what the oil industry is looking at. So make sure when you're discussing geothermal with a service provider, those are the topics, right? Are you looking at these things in a geothermal application, right? And then modeling. You touched on that when, a lot of times we are using API standards. Nothing wrong with API standards, but you know, surface rheologies and rheologies at atmospheric are probably not going to give you too much to bear on these high temp wells, right? The cement, especially if you're using Portland cement, it goes through different hydration periods and temperatures and can get thicker even with temperature, even though we tend to think that it gets thinner. But in that 500-degree well, he was talking about controlling gelation and hydration is very challenging. So modeling and testing your fluids at the pressure and temperature that you're going to be placing it is very key to get lost circulation discussion. What is your ECD really? Is how well are we modeling that in a dynamic scenario, right? These things are an area that we can look at improving in the future, right? And making sure we're modeling high temp, not just the temperature itself, but also the pressure. And this uses specialized equipment that he's talking about. This is not stuff that's, you know, every service company you approach is probably going to have to bring to bear. And if you're advocating for geothermal wells and better placement and to reduce this failure rate, I think bringing those questions to the table and making sure that they're addressed is part of that key discussion, right? And making sure that we're addressing the failures and actually modeling what you're really going to see is important, and that our materials are fit for purpose, and not just, you know, we have maybe have to get away from just using what's on the market or use somewhere else, but what can we bring something to bear that's tailored for the geothermal industry, right? And getting a little bit more specific.
We didn't really talk about, but measuring thermal conductivity. I'm involved in some new exciting work in that area that I can't share the specifics of yet, but there's definitely room to there. I don't think it's been looked at yet because I've been working on it and I haven't found a lot of people doing it. So that's another area.
Absolutely. And the same here, you know, we're looking at, you know, we typically looked at insulation. We're looking at thermal insulating materials, and I think that still has something to bear on some, maybe some of the top strings, but there's a lot to be said on that production string and what you can do with cement, or even more with a non-cementitious, like non-Portland based material, right? And it opens up a lot of avenues. So getting specific towards geothermal applications, take the oil and gas know-how, because there's a lot of similarities, but let's push for some of these to reduce the failure mechanisms. We're going to have to push for more specific tailored testing, more specific tailored materials, I think, for geothermal applications.
Thanks, guys. I want to get Steve on here as well and just ask Steve for his thoughts.
Okay, so maybe go in a little different direction for a minute. We've been using Portland cement for a long time, and as the temperature goes up, we add more silica, but there is a temperature at which adding silica is not going to work anymore, and we'll need to go to a different kind of cement at that point. The other on the Portland cements, when we've excavated wells, for the most part, it's cracked, and it cracks because of both longitudinal and circumferential stresses imposed on it by the casing. And what I want to bring up is they still work fine. we don't seem to have a problem with long-term leaks, even though the cement is cracking. And so we don't abandon wells because the cement cracked. We abandon wells because of some other reason. And so when do you get to the point where that stresses become impediment to well integrity? And I'm not sure we know that. The other part is you drill a well for, it gets to the lost circulation problem. You drill a well for 3,000 feet blind with no returns, and then you need to cement that well after you run the casing in. And that's a significant challenge, trying to figure out how to do that and still have competent cement. So I think, you know, some changes in chemistry are merited. You go up to the supercritical or supercritical temperature, and even if the pressure isn't there, you're looking at production temperatures in the 400 degrees C range. And at 400 degrees C, I don't think we know what's going to happen. But we haven't got any wells that survived producing at those temperatures. They all had casing failures. The two IDDP wells in Iceland is what I'm talking about. And so if we can't prevent the casing failures, which is usually a placement problem, we're not going to figure out how to improve the cement because that's not where the primary problem is. Thanks.
I would add to that all that, excuse me, planning. We so often show up and, well, we've got almost no tools to overcome severe loss circulation problems. And then as Steve was just saying, you know, if we don't get the well properly cemented, we're probably going to have, or we can often have casing failure. So getting everyone involved and up to speed of the critical nature, doing planning, contingency planning for the known problems. We know we're going to have loss circulation, at least it's a high probability, and becoming a little bit more effective in that area could go a long way to improve the overall economic performance of geothermal fields. So I think that's real critical.
A couple of key things that I heard you guys talk about in there is really understanding the properties of cement and being able to expand the technology that lets us determine what those properties are. So then we can make the best educated engineering decision on how that's going to play out in the wellbore. And then the point that you're making there at the end, Daniel, is communication. And isn't it funny how most issues in the world really come down to a communication challenge, right? Whether you're you want to keep it as kind of IP for yourself, or whether it's something that you just don't want to be talking about external to your organization, or if it's maybe just an unknown. And I think that's important, that when we're sitting down talking about how do we make a well successful, that as an industry, competitors, clients, suppliers are all open to saying, how do we make this a success? Because making, whether it's a geothermal field a success or an oil and gas well a success, it creates an answer to the energy demand side. And that is what gives us the opportunity to all go and do what we love and produce wells and cement them. So what I wanted to ask the three of you, and I'm going to go to Jeff first on this one, is how do you think as an industry, or as a group of competitors, clients, and suppliers, we can work together to solve some of these challenges?
I mean, Steve is really talking a lot about, you know, placement and geothermal wells as being one of the key critical failure mechanisms, you know, long before we ever take it offline, because 12 years we had a casing failure, or, you know, we saw some communication surface, or whatever the case might be. If it all starts with the placement, right? And I think a lot of communication with bringing to bear some of the concepts that Daniel said and I've said earlier is, are we looking at our ECDs the right way when you're talking about cement placement? Because the majority of the way we're testing is not really bringing it to bear on a dynamic rheological model, right? And so is that ECD, that frac gradient, you know, like, I mean, our model said that we were below this frac gradient, but was that real? And how real are our models when you're talking about cement placement? And, you know, bringing to bear some other technologies, such as, you know, some of the things that we do, you know, could we bring certain lightweight technology? Could we make a non-cementitious, or can we get a lightweight material that could provide the isolation and placements that we need, and thus, you know, help to control the ECD, you know, discussion, and still be placed in high temp, as well as, you know, bring the mechanical properties that we need to bear, right? Or is it managed pressure cementing? Is that something that we need to bring to bear a lot more? And especially in a geothermal well, where the formations you're targeting are typically going to be on a lower frac gradient side on purpose, we should probably look at some of these techniques, right? What techniques are out there, talking to the market, opening up our ideas and saying what can we do and what has been done to ensure placement in low frac gradient environments, right? And can we bring that technology to bear with geothermal mindset and performance? It's kind of one of my thoughts on something that we could do. I'm also interested if there's anybody else out there that want to discuss some placement failure situations or other things. I think we can bring that to bear in this discussion too.
Thanks, Jeff. I'm going to go to Steve next, but just before we go there, I want everybody, whether you're online or here, start thinking about some questions that you might want to ask the panel, and we'll go to those questions here after we finish giving these guys a chance to talk about industry communication and collaboration. Steve?
I don't think anybody likes to talk about their failures, not openly. Certainly our companies may not want us to talk about our failures, but if we don't do that, we're not going to solve those problems. We're isolating ourselves to our engineers and our contractors, and it's a industry-wide problem. Whether you're working in New Zealand or the US or Indonesia or wherever, we all face that problem. And so I think, I was hoping we get more people talking about failures, and I don't know how to encourage that, but I think if we don't look at, well, we did it 10 times and it failed once, or we did it 20 times and it failed once. That's what's different between the failures and the non-failures, and what can we do differently, and get all the minds in the room working on it rather than just a select group.
Yeah, thanks, Steve. I couldn't agree more. It's tough when you talk about something that didn't go right, because there's reputation damage, there's money on the table, and when we're talking about wellbores, particularly if you're doing the liner job or the production job, there's big money on the table, right? That the risk and the liability is there. That's just placing the cement and getting ready to move into your completion activities and then ultimately production. The other area of failure that just not in the placement of the cement, but we talked about well integrity, we talked about the life of the asset. What are we seeing there, and how are we gathering data on that and taking a look at? We talked about the cracks that show up in the cement, and we're not really seeing a loss of integrity from those. And that's the initial phase. But how does that play out when we're talking about abandoning these assets long term, right? And how do you get your 1 million days worth of containment on that well when you're abandoning it? And all those phases of a well's life are really important for us to consider as an industry. We have a social responsibility in all of those pieces to make sure that we're delivering well integrity. Daniel, do you want to share your thoughts on collaboration and how, as an industry, we can kind of come together and be able to achieve success through communication and collaboration?
Yeah, I've got lots of thoughts going through my mind. One of them was, I think Lou said the most important thing that will be said this morning is, as a drilling contractor, he sees cementing as one of the most critical things being done. Lou understands it, Bill understands it, people who are in the industry. The problem is not everybody are like them. They don't get it, how critical a cement job is. It's often an afterthought. So even though I think 80 to 90% of the problems that we face, there are tools available to solve the problems. The problem is getting the people who understand those solutions and then effectively communicating that through an entire organization is important. And one of the other challenges we face in geothermal is, in many cases, there's only a handful of wells drilled, so you don't get the benefit of the learnings from, say, an infill drilling project in oil and gas where they drill 100 wells and the first well is twice as expensive or less than the last well. So we're working on some projects where we're trying to capture the industry's corporate knowledge and make it available to small operations so that they can be effective. And there's a DOE project that I'm working on with several where we're going to try and do that. We need to continue to think about how we can share with each other the value of the effective tools that we have to solve the cementing challenges that we have. And I think also we need to effectively communicate the dollar value of those solutions, which I think would be key to unlocking a lot of managers into being open to being more robust in their evaluation of their cementing programs, which often they're not. It's often an afterthought, and they don't want to hear about all the new fancy stuff because that just costs money. And then they look at a well that fails on them in 1 year and it costs them a lot of money. So we need to be effective, not just complain about it. You know, I could be a better father if it wasn't for my kids kind of attitude, not do that, but think how we can effectively communicate the value of the solutions that we're providing and think in those terms. I think that will benefit the industry so that we can greatly increase the amount of geothermal production we want in this country and around the world.
Yeah, so true. When you take a look at how organizations are structured and what are the value propositions that you're presenting to the various aspects, right? Drilling has one, completion has one, production has one, well integrity has one, right? And how do you find that that means to communicate the message about the value that you're creating? And there's dollars and cents in it. That's why we're all here. That's why we're in business, right? And like you're kidding yourself if you think there's something else that's going on there. But there's also the broader applications that come with running a good business, and that's showing up in the form of the ESG mandates that we're all taking a look at now, right? And one thing that I find is almost universally true is that if you have a good business proposition, there's usually a good environmental proposition that comes along with that, or the S or the G comes along with that as well, right? When you're taking a look at how you're running your governance or how you're protecting society in there. And so it's changing up the way that we take a look at how we sell value, and being able to get a bit of a broader audience underneath that tent when you're talking about the value that you're looking to present and what you're looking to achieve. That ultimately leads to a positive outcome for the energy sector, regardless of which segment you're operating in. All right. Who's got a question? Oh, 3. All right. Well, I'm going to carry the microphone around. So Lou, we'll go to you first, and then I'll work my way up here through Catlin and then over to Baker Hughes.
You know, the one of the things that, you know, as a drilling consultant, and I know Bill does, and a lot of other people do, and a lot of other drilling departments, is when we present a drilling program or a cementing program, I should say, to management, 9 times out of 10, they're going to pick the cheaper one. And cheaper one is not always the answer here. We need to be able to not only know the difference between the cheaper one and the most expensive one, and the reason why the expensive one is being suggested, it's going to be degrees of success. And we as cementing people need to be able to transmit that information to management and the people who are running the operation, that you need to spend a little bit more money to make this well last, to make this well be a long period of time and not see any failures. And I think it's a lot of our problems in that we don't spend that time. You know, we need to estimate. As a drilling consultant, I need to estimate to you what is the cheaper one and why I would choose the other one. And I think a lot of us need to look at that a lot and be able to express that to our associates and our management people. The other thing I mentioned was, while you're sitting there, talking to Catlin early, we need to, each one of you, you got a notebook in front of you, write down what do you think we need to do to have a success. You know, each one of us write down what do you think the keys are success. And also, what do you think you'd like to see in a next workshop? So we can start looking at those things as well. And Catlin will take, he'll be the source of sorting things through things. So with that, that's all I wanted to say. Thanks.
Did you have a question that you wanted to ask?
No, I'm all right.
Okay. All right. I'll come back here. Go through this. All right. What's your question for the panel?
Thank you. So first of all, I fully agree that geothermal wells are expensive than oil and gas, and they should be like that. I've seen that in over and over in conferences that geothermal is too expensive because of drilling. Well, we do something else. So one of the things I've noticed, and I would like to bring back and hear the feedback from the panel, is two things about particularly casing cement formation as integrity are kind of really missing. And I'm talking about degradation and long-term properties, which actually, if we look at cement, we don't have it. My lab has right now 5 years data of cement, but that's all I have. So if you have a well of 20 years, how you evaluate the well integrity on that? So what's your opinion about degradation of materials in geothermal? Because that degradation doesn't really exist in oil and gas in the level of geothermal.
All right, I'll go first, I guess. But it's a good question, right? A lot of times our data sets and evaluating cement and keeping something under pressure and temperature is going to be, 5 years. That's bravo, because you went through shutdowns and everything else and kept something that was going. So our data typically set is in the years, not a decade, right? And so we have to infer some of the chemistry at temperature and understanding, but we do know there's degradation at high temps, and I don't think temps are going to get any less. And that same conversation is in the oil and gas as well. I mean, temperatures are not decreasing and pressures are not decreasing. In fact, they are going the opposite direction. And the geothermal discussion will likely be the same, and it is. So I think we both hit on this, is that, do we think Portland cement is the material of choice? And is that a discussion that the industry needs to have? Yes. Does it mean that it doesn't have its place? No, it does have its place, and there is, but is it the material of choice for certain temperature ranges or certain conditions? And we're typically not asking that question, but it is a question that the industry needs to ask. And do we need a tailored specific cement for different, or cementitious material for different temperature ranges in a geothermal application? I think you're absolutely right. And the payout, like Lou says, everybody's talking about dollar signs. That payout, so you may be further down the road. Maybe it's not immediately. Portland cement might work just fine in the near term, and everybody believes things are fine, but you might see failure mechanisms appear later on in the life of the well, right? And you're not getting the longevity that you need, and then you end up spending money in the life of the well, right? So it's a dollar value proposition, and a different cementitious material may have a different dollar value, and making sure we communicate why we believe that's important, and also the benefit of that material that might actually have a dollar value increase on the performance of the well, right?
I would, I always need Steve Pye to balance me out when I get off on a technical tangent. He mentioned earlier, we see cement crack all the time and we don't have any problem with the wells. So in a purely technical, theoretical standpoint, that may be interesting. But as I process the question, in my mind, I see more of the real big negative impacts occurring because not because the cement degraded in some way, but because it either wasn't placed properly in the first place. So you get lost circulation during the job, or the casing wasn't properly centralized, or you used too heavy of a cement and you had losses. So that may be technically interesting, but I don't see as much economic impact from mechanical degradation, although it's an area that I'm very interested in studying. So there's two kinds of degradation. There's mechanical degradation, and that's one thing, and that has to do with cyclic stresses. There's also chemical degradation, and we may need new materials as we drill, and we have H2S and acids. I was talking with someone this morning about they're going to replace the casing because it's gone, because the acid removed all the metal. So, but the big challenges in my mind, the things that would bring great value is just getting the cement properly placed in to start with. So those are my initial thoughts when you mentioned that, asked that question. Steve, you can balance that out.
Okay, so we've got wells that have been in production, oh God, since when? The 50s in the geysers and Largarello, and the Salton Sea's been going since the late 70s, early 80s. So there's a lot of time on the Philippines, the fields in the Philippines, and so that degradation hasn't resulted in a catastrophic reduction in life expectancy of the wells. The outside in corrosion from sulfuric acid zones that are shallow, to be blunt, is a problem, and it goes through the cement and it goes through the casing. And the cements we have available, even the refractory cements based materials, don't stand up to that sulfuric acid corrosion. We don't have any material for that right now, not that's commercially available. And so that's an issue of chemical attack that does need, there's a number of fields that are suffering from that. And you drill them out and you re-cement something smaller inside and wait for that to fail and then abandon the well. But it is a problem. And so I'm glad you brought that up. Thanks.
All right. Thanks, guys. Jose?
Thank you. So I'd like to ask you, we've been discussing the opportunities or the gaps that we have and where we can move forward, right? And you've been discussing cement as the main cause, but looking at the whole system, looking at the casing, the threads, the thermal cycles, the non-metallics, everything else that we can do. Could you guys maybe elaborate a little bit more on something other than the cement and what we can do as an industry to move forward?
Who wants to take that one?
I think that's a big one. And Bob Pilko's in the back. He works for Blade Energy Partners. They're excellent. I'll give him a plug because I work for him too. But to have expertise in understanding the interaction between the cement and the casing. And I think it's critical because a lot of the well design people know nothing about cement, and a lot of the cement guys know nothing about casing. And the interaction between the two is the life or death of the whole process. So I think it is very important. I think there are efforts being done, but I think we need to get out of our own little boxes and talk to people and in different disciplines, because it's the overall process. And I think we're just beginning to do that. Having that we have casing models that look at the stresses, but they don't necessarily model the cement properly. And we have cement models that are starting to put the two together, but we really need to look at both together before we're going to come up with a solution that actually works. So I think it's critical. I think it's a good point that you brought it up. I have lots of opinions about it. Bill?
So maybe to address that question. So when we have that outside in corrosion, we end up putting alloy on the inside, so it won't corrode when the acid comes through. but we know the cement's going to disappear in that area. Whether that's a problem or not, I don't know.
Jeff, did you have anything you wanted to say there?
Well, I mean, other than, I think it goes back to having the broader discussions on a well. So like Lou was saying, when you get these progs out to your service providers for cement, casing or whatever, giving as much feedback to those providers on what the failures you've seen or what you're really looking for. And sometimes that's hard to understand because, what are you looking? Are you looking for mechanical properties? What are they? So getting with somebody, like tailoring your progs to be a little bit more specific. So when you get a lower price and be more holistic, I guess is the word, with casing, with cement, with casing hardware, what can we do during the cement placement as well as rotation? What's the stresses? Can we rotate pipe? Is that really going to help us out here? All those components in one place and getting them to talk to each other. I can't tell. I've been in cementing for almost 16 years now, and I have never once went in with a casing company to figure out, hey, what's really your practical casing movement under these cyclics, right? What have you modeled? I have my model, but I'm not a casing provider. I'm a cement provider. I've tested that thoroughly, but getting a more holistic approach when you're really looking at one of these one-off. I mean, you look at your projects, you got a very small window of to get it right, and a failure is just basically unacceptable in economics. It makes sense to be a little bit more holistic in our progs, right? I think is kind of what we're getting at here, is bringing the whole group, right? And instead of being in just a cost competitive environment, but being a value competitive environment, right?
I would also throw in again that geothermal is the same as oil and gas, only different. Oil and gas wells can pay for themselves in a year, and we need geothermal wells that last at least 30 years. So it's different. They can get away with the crappy cement job, and they're going to pay themselves out. And because the energy is so it's so concentrated that they can get themselves paid off. For geothermals, it's a different mentality. We need these things to not only build them and get steam for 6 months, but we need it to last for 30 years. So we need to carry that mindset with us every time we interact with the various members of a drilling team.
Thanks, guys. I think that was an important comment at the end there, in that the value proposition is potentially different between what asset you're going after, and making sure that you understand that value proposition is important for achieving success. Yes, I will get to you.
Yeah, so I think for those who are in the oil and gas industry, we're married to a power plant, and the power plant life is 30 years. And we have some legal liability if we can't supply steam to that power plant for those 30 years. And that's different than oil and gas, which is selling into a fuel market and not directly to an on-site power plant.
A question and a comment is, I think we have all heard since the start of this workshop is that cement is the life of the well. One of the things that we have seen in the industry, and I think, all across, both from the operator side as well as the contractor side, one thing is that you see cost and value. And when you're preparing a budget, you come up with a number like what Lou was talking about. And the moment that value is put across to through the levels of the organization, once it comes up to the financial level, things change a lot. And then again, you have seen that I'm seeing in both developed countries as well as developing countries, that when normally contracts are opened, the proposals are opened, first the technical bid is opened, and then, oh yes, you got 80% or 90% technical qualification, and then suddenly when the financial is opened, all those 90% goes off, and the 10% that was the financial holds the key to that contract being awarded to the whichever service provider is there. I think that has to change, and I would like to get your opinion on that. And the second thing is, we all talk of, as Steve was talking about, failures. Again, we are all bound by non-disclosure agreements that you signed. Now, how do you work around that to be able to share the knowledge that you've got from a failure so that you do not repeat it again. We do drill well on paper and lessons learned, but does it add any value to that if you do not share your failures? Thank you.
Yeah, so I think, I think we all agree we cannot ignore economics. We cannot ignore economics in our own companies or our own segments. But I think what we have to do a better job, as Lou and Daniel really said, is communicating the value. It's more than $1 price on the prog. And if you're oil and gas, the AFE, right? For this extra 10%, 15%, what is the value that you're getting, right? And what is the real payoff? What's the risk factor? If you're losing 20% of your wells on placement and you can move that to 100% placement success, what's that value, right? And why, like Lou said, communicating why in a much broader scope. And when we go out there and solicit, bring in some communication, bring in some reasoning why, right? Don't just give a dollar value and say, I have a $1 value one for cementing, $1 value two cementing. I have a value proposition here. This includes this, this includes this, right? If you're going to get a car, you're like, oh, that one has, power steering. That one doesn't. The one that doesn't is cheaper, but I can only drive the one that doesn't for about 10 minutes before my arms give out, tying value with cost,
Daniel or Steve, did you have any comments that you wanted to make about that question? If not, we'll move on to the next one.
I'll make a short comment. I agree with what was said. The problem is doing that quantification of the value. So we can all rotate the strings if we buy the right connections. We can reciprocate the strings if we have the right connections and pipe, and yet we don't do that very often. We'll run a stab-in job, and we don't take the extra steps required to be able to rotate or reciprocate the pipe. And I'm just giving an instance. You can go through a lot of it where if you don't have data to show that you're going to improve the value by doing that, even though you know that that's the way it should be done, then you have trouble selling it to management and on any of these things. So it's understanding where that saving is in spending more money.
All right, thanks. We have a question from Simon online here. He wanted to know, how do we efficiently de-risk new technologies as we bring them forward, especially given the challenges that there's a limited number of people that want to be first. Certain areas you maybe don't have that volume of wells to kind of spread that technology test over. So how can we overcome this challenge where people want to see real world results, but nobody wants to be the first to deploy that new technology?
So we used to have a geothermal drilling organization as part of the GRC, and operating companies as well as vendors of various services belonged to that geothermal technology organization. And the operating companies took turns volunteering to be the guinea pig, because that's what you're asking for. Somebody's got to volunteer to be the guinea pig, and it's liable to cost money, and it's liable not to work. And so how to share that guinea pig requirement becomes an issue best served by making it a cooperative project as part of the geothermal drilling organization, which of course doesn't exist anymore.
You may also try strategies like, offering, hey, if this works, then you're going to get a special deal for the next 50 wells. I mean, it is a challenge. Yeah, the next 50 wells. That's what I mean. Well, the next group of wells, whatever, there needs to be some type of economic incentive. And I mean, as you said, that's a tough nut to crack, but that's maybe one way to try and address it, is offer long-term benefit to the first guy who tries it.
Okay. Yeah.
And just try to lean on anywhere else you can to look at what success stories are in similar well configurations, right? In oil and gas or disposal wells or whatever the case may be, right? And lean on some of those industries to maybe vet some things that have that quicker payoff as best you can. However, geothermal is different, right? So you got some areas that can be hard, but there are a few high temp plays out there in the oil and gas industry, even though they've taken maybe some back seats in recent years, doesn't mean that they haven't been done. I mean, even in Mississippi, who are no one's even at now, they had some really hot wells. P&A to well in Mississippi that was 500 degrees Fahrenheit circulating in the last couple of years. So there's some bringing to bear some of those lessons learned and just trying to do the best you can as to learn from other industries that have a different risk profile, right? The geothermal industry might have.
Yeah, and it doesn't have to always be a high temperature well. It may be a technology you can try. Working with oil and gas operators that would be effective and you could transfer over with minor adjustments.
Yeah. Just a reminder, if you're not talking into the mic, the people online can't hear you.
Yeah, just to say you may be able to try it like we were just saying with an oil and gas operation. And that's why we maintain our communication with both sides of the aisle, that we know what's going on in both industries, and there may be application in oil and gas. I'm working with an operator in a service company in South Texas. We talk about this all the time. So maybe trying it in oil and gas or some other one-off operation that we could then de-risk it there and then bring it to the geothermal industry.
Yeah, for sure. Crossover industries, maybe not even underground, right? There's lots of cement that gets placed around the world, and how can we kind of capture ideas and cross-pollinate? And I'm sure if our government friends were here, they'd also say that they play a big role in helping bring new technologies to the industry. I think back to SAGD in Canada up in the oil sands, and how the government led a project around how do you successfully develop that technology. And then once it was developed, the industry players were able to make that a commercial success. All right, Bill, question from you.
First, sorry about that. That's one of the things that I've really come to recognize recently is, you know, we're not just an order of magnitude smaller than the oil and gas industry. We're at least 2 orders of magnitude smaller industry. And, you know, I've been around drilling 50 wells in the last 5 years for all the clients that I have. It's so, although I have a client right now who's talking about drilling 100 wells in the next 10 years, and it wouldn't be the first project that I got on. You know, here's a 20 well project and we drill the 19th and 20th well first. So, and I have a comment too. I can't recall. I think it was in the 50s when BC McCabe drilled the first commercially successful well at the geysers. And that was drilled rotary drilling and not cable tool drilling. And that casing was cemented in place, but I'm sure he didn't even have any silica flour in the cement. And that well is still producing. Well, it was still producing the last time I drove past it. Now, one of the things that we're, one of the functions of the cement in the annulus is to support the casing. And in a lot of cases, I guess I don't care what's in the annulus, just so I got the shoe cemented. I don't give a what's in the annulus, just so it'll support the casing. And I don't really know what my question is, but and it does lead into the, you mentioned writing down ideas. One of the things we need to do, especially in geothermal, is talk about mechanical placement of cement in the annulus. That is at least as important as anything else, in my opinion. And I don't know what to do about it, and that's why I'm talking about it. Thanks.
I can actually answer that even if it's not a question, because I've got some thoughts. First, we're going to talk about some of the mechanical placement, and I definitely hear what you're saying, Bill, about 50 wells. We haven't done 50 wells in 50 years almost, because they're usually small projects, or if they're single projects, they're very big projects. But the flip side is, I see my other half of me sees new startup companies that are looking at new ways of developing geothermal power and extracting it. And they are thinking in terms of their first well, but they're talking in terms of 50 wells. And it's not just one. So I think that's really actually exciting and good news, that it's not just, hey, there's going to be a lot of wells and there's going to be hopefully a lot of renewable power coming from that, but it's also going to be an economic opportunity for everyone in the room here. So it's exciting. And this is really maybe an inflection point in the industry. Of course, we've all heard that before, but yeah, I understand. I feel you totally, Bill, because I've been with you in the trenches doing the one well and trying to just get them to do that one right. But there are people talking about, when you start talking about 50 wells, then we can start talking about learning from each well and bringing those learnings, because we're drilling them in the same field, reducing the cost of those wells, probably 40–50%, possibly.
Jeff or Stephen, did you guys have anything you wanted to add? General comments? If not, we're going to go to Susan for the last question of this opening panel. And from there, we're going to go to a coffee break after that. So Susan, ask your question. We'll give all three of you an opportunity to answer. And then thank you for your participation this morning.
Well, thank you. And my question is more of a statement, and that is, CERC's perfectly willing to share our cementing failures, because we think that in order to solve these problems, we've got to be open about what's going on. And just to tell you right away, a lot of the failures we see are up in the shallow subsurface, and we do see outside in corrosion, the cement goes away, and then our casing is attacked and it goes away. And, if it's really shallow, great, we can dig it up and we can do a repair by replacing the casing, and then we can put some cement in around it and hope for the best. But these things happen over and over and over again. And when you're going out there digging down 47 feet to do one of these shallow casing repairs, you realize this is not only expensive, but scary sometimes if it's a high temperature producing well. And this is not an easy thing to deal with. So, we can say cracking cement isn't a problem, but cracking cement is a problem. It allows that acid water or oxygenated water to get through to the casing. It allows the cement to be dissolved, and we have to figure out ways to fix it. We have other kinds of failures, and you can say, oh, well, that was a casing failure. Casing connections failed. But you know what? The casing connections, yeah, maybe they did fail, but why did they fail? It's because one of the functions of cement is to support that casing. If the casing's moving around in there and, it's then stressed in ways that it wasn't designed to handle, because the cement's not holding it in place and not giving it that support. So I think that as part of this workshop, I'd really like to see us all be open about the failures we've seen. And I'm happy to start the process. Anybody want to ask me about what we're seeing? Happy to talk about it.
Thank you, Susan. I was glad you got to ask that question. What we've heard is like, is cracking a problem? Is cracking not a problem? Maybe certain areas, maybe not. It just depends. There's a lot of factors that go into that question, right? What fluids are they allowing to communicate where, or what corrosion environment are we in? One of my jobs out of Schlumberger that has been for the past 10 years is training young cement engineers. You know, yeah, you got your degree now. You don't forget all that. Now I'm gonna teach you how to be a cementing engineer. That's a lot less glamorous than what they probably told you when you hired on. And we, you know, here's your hammer and go on a rig for a few years, right? But the first thing we tell them, one of the first 3 components that we tell them is cementing is there for casing protection. That is one of its key functions. And when that goes away, you lose that protection. And also what cement you're using, there's different levels of protection and permeabilities and all these other different things that can come into play, right? So those conversations, right? And if it is failing and cracking, cyclic loading is, you guys, temperature is probably one of the worst cyclic types of scenarios that y'all are using on a constant basis that has a lot of effect on cement sheath failure and like allowing that communicate up the surface and then have surface issues through corrosion, right? And I think that's a big challenge in communicating it. Now, like you said earlier, there's some answers out there, but how we communicate and where do we bring, you know, making sure we bring them in is a key component of that. You know, we need to communicate more openly throughout the industry. So we bring all the ideas on the table so we can come to the right solutions.
I would just, it's not really a question, Susan, but I would just throw in, ask for help. Because as Susan mentioned, there's cases where when it cracks, cement cracks, you lose your well, and you have not only expensive, but scary, life-threatening situations. And then as Bill and Steve mentioned, there's wells that have been 30 years and haven't had a problem. So if you're not sure, ask for help. There's people in this room. I will take a call any day of the week, just about any time. Be happy to help anybody with the problems. If I can, you know, wake up from whatever. But there's other people in this room. There's a wealth of experience. Don't keep going down the road and go, well, I hope this works. So there's a lot of people around. We're a community and we are happy to help each other. And you know, we'll eventually make money from this situation. The main thing is to get your problems solved.
So on your problem, Susan, the shallow stuff, we see 2 kinds of external corrosion. One's shallow, where it's not protected from the aerated fluid that's in the ground. And that's normally protected by running the outer casing string that's outside of the production casing higher, and so that it doesn't end up with water intrusion into that cracked cement. And the other one is usually deeper than that, and it's acid corrosion. And acid will eat through the cement whether you've got cracks in it or not, and particularly sulfuric type acids. And that's a whole different problem, because the cement's just not going to hold up whether it's cracked or not.
All right. Well, again, thank you to all of our panelists this morning. Thank you to the audience for the great questions. That concludes our opening session. We're going to take a half-hour coffee break here. So let's plan on being back at 10:30. And we're moving into our first set of presentations then. Thank you.
What is it? It is the Teodorio bonding. Yeah, this one. Yeah, the other one is for later. Is for tomorrow. I'll bring it tomorrow.
Okay.
It's not just conventional, but
Hi guys, I was trying to find my phone not to speak. I mean, I have so many answers. If your casing connection fails, it's because you use the wrong casing connection. Casing connection is specified.
Yeah.
So I know what a good connection is. I can tell you the guy who needs 5 connections on the market will never fail.
But they have to use it.
Correct. And I don't know how to convince them to use it.
Well, that's why we need to have this discussion with the casing people. It's not just a cement problem. It's a total well design.
But also they give it the lowest common denominator. The service company knows if I give it the same reason I'm hitting against somebody, they're gonna lose that price not away. So they can put that in the hours out.
Well, I'm working on projects where we're not looking at.
You gotta look at this, what does the valve, what's this valve?
So just because there are people doing that, realize those are probably the ones that aren't being successful.
The company department never understand.
Well, again, it's, I could be a better father for my kids, you know, or maybe I learn how to better value sell, or I find customers that are. I am working with one of those, and I know there's multiple out there, and I can tell you, I'm not looking for cheap.
Not looking for cheap, but just for something that has very specific.
The value of success is now in this one company, it's so apparent that we're willing to spend the money to get it out.
Let's say if you open up your novel, you're going to be telling like why does what if you do?
Well, yeah, but imagine companies that should get upset. So I was talking with a company and I told them, why the heck are you using API connection in long horizontal wells? Because the API connection has never been designed for it. So you have to now. So I did that in 2015. The company actually refused to talk to me after that. They were not even coming from my students. They were so mad at me. 2020, I was invited in the FPA workshop to talk about fractures and failures of coupling connections in horizontal wells. And I said, well, I know why they crash. They crash. They are API. That's your problem.
Yeah. But there's the one company that's going to blow you off, and there's the other company that's going to hire. I spent 2 years in Australia because I gave them a solution, and they go, you know what, that's right, we want you to come along. So there are the ones out there, and it's also the general philosophy I want. The most successful project I went on, the well was twice as expensive. But because we were successful, we could then drill the second well and then know for sure how to optimize and then how to cut down your cementing costs and everything else. But a failure isn't worth a nickel.
I know. I mean, I had, I did a lot of foundation on gas wells, and so my well was about 1.5 more than the condition they have. But my well was the only one of this. So the company says we're going to do everything now using global because we don't want that taking well. I mean, they had like 20 different wells. All of them done according to standard, conventional.
And I just got done with an oil and gas company that are very protective, but are very observant of how they're drilling. They have their own drilling. They do their own drilling. So, but they really do focus on detail, and they are still in business. And actually very successful. I just want to encourage you because I've been on the server side and I've been told, oh, I spit on my documents to where this would be done. Just let it roll off your back. There's going to be other companies that really value your solutions. I'm learning more about plumbers recycling. Yeah. Just keep putting that your best stuff out there because that's the stuff that's going to be valued too. It's successful. Yeah. But we do, on one of my first talks, we have solutions to most of the problems. We don't need a lot of rocket science, but we need to implement it uniformly.
Honestly, with all the wells, how to get well team in place, that's very well done.
How many people follow best practice? How many people run an outside power?
How many people subscribe or
Good to see you too. So, who did you deal with the BBC? Who was your field contact for operations? Willard is a technical guy or a money guy?
He's the guy. He's the guy that I work with.
Oh, really?
Yeah. So Willard's the.
Okay, so Willard's the main guy.
He came out to the section. He was in charge of everything. He was there.
Well, there's a meeting this afternoon. That's the right time for the meeting. We need to do a schmooze and we need to. I know. That's what he still won't pay the fucking excess over that. He just needs rubber discs, I guess.
Willard is
he is the guy.
He will work, but when we need it stuff, he works out taking care of it.
Yeah.
But he's
been cut out of we bypassed it and moved all together. You purchasing, he's going to approve the payment.
Because Andrew had more on site there.
There's like $6,000. Not, yeah, but not less than the final. Not once we put our markup on it, it's $6,000 more than whatever the contract is. Wow. Let's see that.
Most of them. But there are people who do it. And we found ways to get
you know what? Really, one of their
we have solutions.
That's okay. So Cal Energy has 70 wells over 35 years. Oh yeah, the CTR is talking about 100 wells in the next 10 years.
That's all we don't go to the last hole.
I think they got money for two.
Saudi Aramco, are you involved in, there's several guys that I know who are in the cement side over at Saudi. I worked with. Good. And are you yeah, are you
I last 2 years I've been curious about the challenging thing.
You don't want to.
Yeah. Right. Well, I actually just saw yesterday about all the geothermal potential. And the known projects. Well, I'm working for a company that where we don't need producing food. Cutting edge technology, but the day for Aramco to know about, for the non-profit, for Western desalination, we're focused on extracting. Like a story for power generation, agriculture, so there's actually depending on thinking about that, and it will involve
I have my main session
I've actually worked on an energy storage project where it's shallow and they had a total failure on stuff and they hired me because we know what to do. It's just they didn't come in to do that. So they got to the point where they were willing to so it's doable. But yeah, low temperature. Are you going to say what's all the right? So that's not a big. You gotta be one or the other. You know, how are you and that will involve
you're not going to see
You know, that's why it's not gonna- the minute she says, I don't-
It's went okay. Yeah, I'm surprised. It's usually like we try to pull teeth, get people to ask questions and participate, but we also, yeah, we also, that's what we
this thing will- it's got 3.5. 2.5. The other third build that's in the ground is almost quarter slab. This was, and they built 2 of them. First, we never even got it installed. So we did this. It's still in freeze.
Yeah. Yeah, certainly. Yeah. Looking forward to it. I know it's quite a long time. But my client for it. Looking forward to it.
I mean, it's in the state that is fair.
Yeah.
If you did sort of stand.
Well, am I right? Are the costs
Yeah. Yeah. Yeah, absolutely. We've had a number of projects directed toward interest in reclaiming some of that H2 space, but technology. Curious. Yeah. Well, you're yes. Well, yeah, I've been a big part of it the whole time. So it's not the papers. Who's the security? Curious. So I guess, yeah, thanks for sharing the session. You guys are not. We do have some Haliburton folks there. Yeah, with the technology.
Good, good. So I just thought we ought to discuss how we should divide up. I think it's sense. You know, what I want to do is just talk about it for a few seconds, just what is the purpose of this.
Sure. Yeah.
You know, say that, if that's what this session is. But then we introduce the panels. And then how do you want to divide it?
Well, depends. Do you want each of us to start initiating the questioning session and then push it into the audience? Yeah. Okay. Yeah. Yeah. I mean, maybe just to for organization purposes, say whoever introduces, maybe start the questioning and then we kick it over to the other. That's fine. Do we have any? Yeah.
No, we don't have buyers. I was going to just introduce them and then let them.
Sure.
So.
Okay, very good. Yeah, no, it's not good. Should be.
Did we take any good licks this morning, Susan?
I think so. I think there's something about talking about.
Very good.
Is the campus full of people again?
No, it's not. It's still pretty empty. Campus is
overseeing the process. That's right.
Our laboratory.
Yeah.
You still have the same area of responsibility, or has that?
Yeah. It has, yeah. I think probably when the previous year was speaking.
Maybe I'll hit it. Because I'm going to talk about it now. Well, there's maybe not this story. I don't know. So I know that we were worried about traffic, that we were about carbonic acid. So there are solutions.
Right.
So I actually Mario.
Were the wells failing?
Yeah, no, I appreciate it. I think we're going to have to.
I don't say it's really a springboard. 90% of them are. I'll say it.
Yeah.
Did you see, you probably read it around the other. You know, I worked for him for like 6 years ago. So I spent saying this. Right. About a year ago. We found we handle slides. They're
I understand you'll be moderating the panels.
The next one is going to be Susan and Chris.
But they'll be presenting the project.
Yeah.
Well, I'll give you the slides so we can do as we did before the Q&A. So.
Okay. Yeah, I can walk around to that. Okay, excellent. One of you guys have lines.
How are you? Yes. Yes.
Yeah, that's gonna
Where's our
Can you come up? What's your name? Okay, let me find out. Let me just go over there to turn on the microphone.
Hello, everybody. We're about to get started here. So if you could take your seats, we will kick off our first technical session.
So I think we're just about ready to start the next session. And this session, we're going to be talking about the function of cement in wells, and particularly where it relates to high temperature cementing. So I just want to say that when we talk about this, we want to keep in mind what it is the cement's supposed to do in our well. The first is, and I look at it as the 3 S's. So it's supposed to seal. We want to keep the fluids that are inside the well, and we want to keep the fluids that are outside the well. And the cement and casing, that's what they're there to do. So then we also want the cement to support the casing. It needs to provide support for it, and particularly in these high temperature wells, we're going to have thermal cycling. There's going to be expansion and contraction of that casing, and that support is an extremely important function of the cement. And then the third S is to stabilize. We want to stabilize the formation and keep it in place so it isn't falling into our wellbore and filling it up with formation solids. We also want to be able to stabilize any lost circulation zones that are gonna lose our drilling fluid or allow fluids to come back into the well that we don't want to see there. So that's another function of cement, maybe not related to casing, where we're doing sealing of those zones. So we're gonna have some folks talk and give some presentations. We want to bring our first presentation up. We'll go ahead and introduce the first speaker, and I think that's Daniel Bohr, right? And so Daniel, I'll let you give your bio. I know what it is, but you know it best. So we'll let you take over.
Should be technical challenger surprise. The second from the bottom.
All right. My name's Daniel Bohr. I've worked in oil well cementing, geothermal cementing for 39 going on 40 years. Started out working for Halliburton in their technology center, spent 17 years working various positions there. Then went into field operations, spent some time in California running a lab, and I ran into people drilling crazy things like geothermal wells in the Salton Sea. Met Susan, some of y'all here. Then went to work for Ultrarock with Susan for several years. Spent some time in Australia working on a project there, worked for Blade Consulting, learning about casing design and cementing oil and gas wells at 450 degrees, which was exciting. And I've been doing various projects as an independent consultant for the last 4 years. I'd like to thank others involved in putting this presentation. It was not just me. Susan, thank you, and Mileva, Tatiana, and Axel are working with Curistech, and I'll bring them up as we walk my way through here. So consider this kind of an introduction to what we're going to talk about the rest of the week. We've already had a little panel discussion. We're going to go into a little bit more detail on some of the cementing super hot geothermal wells in the 21st century. Little overview, understanding subsurface conditions. What's the difference? Like I said earlier, it's the same, only different. Cementing geothermal wells versus oil and gas. And looking at current cement systems, what do we have? What do we know? And then look at issues like mechanical stress failure, not just whether it's hard, but does it fail mechanically during the life of the well? As brought up, how do we make sure that we get the cement in place in the first place? Talking about placement issues, talking about what happens when we get to 1,000 degrees and Portland cement isn't going to work anymore. We'll talk about alternatives for these super hot conditions, and then we'll wrap it up with some conclusions and some recommendations. So overview, conventional oil and gas, typically limited to 200 degrees Celsius, covers 99% of all the oil and gas. We're just getting started when we're doing geothermal at those temperatures. Typically oil and gas, the 450 degree project, we are looking at specific gravities around 2.3. Geothermal, we want light or lighter because typically we have lost circulation. So our goal is not to control the high pressure oil and gas reservoirs, but it's to ensure that we get cement from top to surface without having lost circulation. So again, it's the same but different. Super hot wells may get as high as 400 to 500 degrees C, and I've started to see projects that are approaching those temperatures. What cementitious materials are going to last or perform there, and which ones aren't? So there are many challenges and technical operationally to successfully drill and cement hot wells. Not only does it need to look good in the laboratory, but the operators need to be able to apply these things. So we need to have a good handoff of these systems into operations that are feasible, not just theoretically possible. So the purpose, again, of this presentation is to just give us a general overview and talk about these general issues, set the stage for the week, so we hopefully have some good conversation. So the difference in a geothermal well versus oil and gas, well, the holes are a lot bigger. The reason is we need to produce a lot more fluid to be economic. So we may be looking at production strings of 7-inch or larger to allow for the flow of enough steam and or hot water to surface to make the project economic. Oil and gas well, I just cemented a horizontal casing 5-inch. Get plenty of energy out of a 5-inch casing for an oil and gas well, never work in geothermal. So we're looking at large casing strings. The other difference is we want all the geothermal wells to have all their casing strings cemented all the way back to surface. We need to have mechanical integrity. Conventional geothermal well, the surface is 80 degrees. When you put it on production, it is 500 degrees Fahrenheit, 250 Celsius, whatever. That's a huge stress on the casing. If it's not held in place properly, you can get all kinds of mechanical failures in your casing string. So objective number one, the way I like to describe it is the most important part of an oil and gas well is cementing across your production zone. And really the most important part of cementing a geothermal well is surface, getting cement to surface. We're not producing, we're typically producing open hole. There's aberrations of geothermal thinking of producing through cemented casing, that's fine, but the majority right now is open hole case through slotted liner. So we're not looking for oil and gas, we're looking for hot rocks. So our geology is obviously going to be different. That's not my area of expertise. Many of you, for you it is, but we're looking for high thermal gradients as shallow as possible. Obviously, the shallower the resource, the cheaper it is to go after and get it. So there may be acidic issues with CO2 zones. Steve mentioned earlier, they have problems with sulfuric acid on some of their casing strengths. These are different challenges than you often face in oil and gas wells. So my favorite thing, well, maybe not, ordinary Portland cement. It's a necessary evil, maybe is a good way to put it. So their advantages, we know a lot about Portland cement. We've built buildings, you look around, everything, you'll see something made out of concrete. And we know a lot about cement and its hydration process. It's readily available. It's been produced. Earl P. Halliburton used it because it was probably available at the, some local store. And he cut sacks and put it in a well. And here we are today, 40, 50, 100 years later, still using it. So it's readily understood. And for most oil and gas applications, there's not a lot of severe temperature challenges. There's not a lot of shear stress challenges. So it's worked pretty good for a lot of applications. But there are some concerns, especially when we start talking about geothermal. It has poor, I should say, no resistance or very little resistance to acids. It dissolves and goes away. That's really not good if you're trying to protect your casing. It's very hard and it's also very brittle. So it's not ductile when the casing goes through cyclic stress loading. When you put a well on production and that surface casing at 80 degrees goes to 500, that casing expands, you put a lot of tensile strength on the cement and it doesn't like that. And it usually cracks. Whether or not that's a problem, we'll discuss that later on. So it's not resistant to stress loading. Poor bonding, it's not ductile, and once it's broke, you can't, it usually doesn't fix itself, not by itself. There are some new technologies that will be discussed later this week, talk about how we can fix that. Chemical and thermal durability, OPC, as I mentioned, it's not resistant to CO2, so when it dissolves CO2 in water, you got carbonic acid. Other acids dissolve it, so calcium silicate, not resistant to acid. Other systems might be calcium aluminum phosphate systems. Other calcium aluminate cement systems can be resistant cement, but these aren't. Thermal durability, we think the upper temperature range is around 750. It's hard to nail people down on that because I've tried doing that, but it's probably in that range. As cement is exposed to higher temperatures above 110 degrees Celsius, it goes through a crystalline structural change. And if you don't have enough silica present, it will transform into a weaker, higher permeability material. And if you do have enough silica present, it will stabilize the strength, turn into torbamorite and other forms that will remain high strength and low permeability. Testing. So we need to make sure we can mix the stuff. We need to make sure that we can pump the stuff. We need to make sure it gets hard. And most conventional laboratories that test cements are good to about 200 degrees Celsius. And for most geothermal application, that's going to be adequate. When we place the cement, we're typically circulating a lot. The wells cool down tremendously. It may be 500 degrees static, and it may be, I keep using Fahrenheit, excuse me, maybe 250 Celsius, and may cool down to 80 degrees Celsius when we place it. So most of the time we can test it. So we need to test the mixability. We need to test the fluid time of the cement, and we need to test when it's going to set up. And most of our testing equipment will cover that. When we get into super hot, as I mentioned earlier, we were looking at temperatures of above 250 Celsius, I believe, 540 degrees Fahrenheit, circulating temperature. And we're starting to push those upper limits, and we're going to need test equipment and chemicals to retard our ordinary Portland cement and some of these other cement systems at those ultra high temperatures. Placement issues. This was brought up earlier as well. It's great if you have the most fantastic cement in the world, but if it never gets in the proper place, it's not really going to do a lot of good. one of the big challenges in geothermal well cementing is getting an entire column of good cement covering the entire circumference of a well bore. And most of the solutions to these problems, we know the answers. It's just we need to consistently apply the best practices and have everybody on board a given project support applying those best practices and not cutting corners, not throwing the centralizers in the mud pits because they don't think they're of any value. So the basics of that is we need a conditioned drilling fluid. That's really not typically very difficult in geothermal wells. Although as we get hotter and hotter, we're going to have to study what are the fluid properties of these drilling fluids at high temperatures. We need to, we may use mechanical aids to help in the displacement process. Centralization of casing. If it's the casing is laying up against the side of a well bore, you're typically got some deviation or dog legs. You're not going to get good circumferential coverage of the cement. And if you don't have that, and especially in pipe and pipe, and you leave pockets of water, you could have a total well failure because you didn't put the right number of centralizers on your pipe. It's not a very good return on your cost savings there. Fluid velocity is important, although not as critical. And we're typically using some type of flush and spacer. So we not only need to know what the things are to do, but we need to properly model these. So here's an example of a displacement model where we're predicting that, yes, we get cement all the way to surface, but because the casing wasn't properly centralized, we have a large channel on one side of the pipe. That would be a poor cement job. It will not provide zonal isolation. But again, we know what to do, we just need to do it. Other thing that's very important, and I'll just briefly touch on it, modeling the bottom hole circulating temperature. Using API, you can take your API manuals and set them, not in the garbage can, but don't use them for geothermal wells because they're not applicable. We have much higher temperature gradients, and you really need to do proper thermal modeling to know what the temperatures are to test your cements. And that's actually a big deal. And as a result, you may have actually different conditions in your actual well application than you modeled for. So as some free advice, don't put your retarder in your dry blend. Always put your retarders for your cements in your mixed water, because you may want to need to change that right before a cement job. That was free. That wasn't even in the program. Other placement issues. Law circulation is a huge challenge in geothermal well drilling operations. Often you're drilling through fractures. In fact, if you don't have law circulations, odds are you probably don't have a productive well. So, but there are sections where you'll at least have a risk of law circulation. And the big challenge is, how can you get a full cement column if you can't even circulate your drilling fluid? So there are a number of technologies available. One is run a foamed cement system. You can foam the drilling fluid ahead. We use aerated drilling. We can use aerated cementing. Only we need to use proper surfactants to stabilize it. Another way is reverse circulation, and another way is reverse foam cement circulation. So I'll just briefly mention, when you pump in reverse, there's multiple advantages to that. When you pump in the reverse direction, the fluid that you're lifting, which is will be the controlling factor in the pressure in the bottom of your well, is your drilling fluid. So if you're always lifting a 9-pound fluid out of your hole, the ECD at the bottom of the well will always be near 9 pounds per gallon, even if you're placing a 14-pound per gallon cement. So I may say that twice to make sure it sinks in. You can give an ECD of 9 pounds per gallon while you're placing a 14-pound per gallon cement. A great advantage. And you can challenge me on that anytime. But the modeling shows that. The other big advantage is you can set your retarder loadings in stages rather than retard the entire column of cement. We had one project in Australia. They had 13,000 foot hole, 4,000 meters. They retarded the entire cement. They pumped it conventional down, top to bottom. The cement at the surface never set up, never set up, because it was retarded for the bottom of the hole temperature. As a result of that, and the high strength casing, the well actually failed and it had to be replaced. And I got to go live in Australia for 2 years to do that, which was fun, but it was not really fun to spend the $50 million to replace that well. So to be able to stage a retarder allows you to retard the cement at the bottom, then the cement at the end of the job as you're going down the annulus. It doesn't need any retarder. And so the entire column of cement will set up readily after placement. It's a well-established techniques. There's a few little pluses and minuses to it, but it's available to the industry. Move on. Whoops. How do I go back? Oh, mechanical stress failure. Okay, we get the cement in place. That's great. We've got the right cement. We have all the right chemicals. We even apply best displacement practices. So everything's great, right? Well, now the cement has to endure thermal stress cycling. And there's been some discussion earlier indicating, well, maybe sometimes it doesn't matter if the cement cracks. Well, I can say there are probably some times when it does matter, and we need to look at that closely. So when we cement casing string, production string from top to bottom, the cement at the surface may be at ambient temperature, but when the well's put on production, it goes up to whatever that production temperature is. That causes the casing to expand radially, and it puts a tensile load, not a compressive load, but a tensile load on the cement. And cement without rebar is not very strong under tensile load. So there's a high probability of cement failure in cement strings, and especially in high temperature geothermal wells. It can happen also if there's stimulation in oil and gas wells. It can happen when you do pressure testing on your casing. It can happen under a number of conditions. So the question is, how do we prevent that from happening? I'll go one more step. This just shows the types of failures. We have radial cracking. That's in the upper corner. I'll point to it with my pointer. That's due to tensile failure. We can also have debonding from either the rock or the casing, and that can be a bad thing under certain circumstances as well. So how do we prevent that? Well, we need to look at the stresses that occur in the cement during the life of the well, as it's placed, when it's completed, when you put the well on production. And we found one of the highest stress conditions for cement is when you maybe do an acid job to remove scale during the life of the well. You're pumping cold fluid and all of a sudden you're shrinking that casing, puts a lot of stress. So there are models available commercially, some of the large service companies, there's other independent companies that have models. The main thing is you have to model the stress cycles that the cement's going to go through and determine whether or not you're going to have compressive failure, tensile failure, or debonding. And I'll just touch on it at this point. We need to know we need to know not only, oops, I'm going too fast. Not only know the properties of the cement, but we also need to know the geometry of the well, the properties of the casing, the properties of the formation. I did analysis on essentially two similar situations. One was a steam injection well with very soft formation. The cement failed. I took that same cement and put it in a geothermal well with granite or very hard rock, and the cement didn't fail. The problem was the soft formation allowed for deformation, expansion of the donut of cement, and allowed for tensile failure, where in a geothermal well it didn't. So all those properties are critical. Scent failure prediction. Yeah, like I said, depending on wellbore geometry, casing thickness, temperature changes, pressure changes, formation, mechanical properties. And we have to predict this during both the drilling, completion, stimulation, production, and I would say workover conditions. So we need to look at all those things. Cement failure consequences. It was discussed, there's wells that have probably had cracked cement in them for multiple years and they haven't had a problem. There's also wells that I know of that have had cracked cement and they did have problems. So when it is a potential risk, we need to apply the proper tools to analyze the problem and come up with solutions to that problem. Okay. Cement failure, geothermal versus oil and gas. There are differences. When you frack a well, which typically is not happening in a geothermal well, you're putting a lot of stress on the casing. You may have failure there. In geothermal wells, you experience chemical changes and phase changes in the cement that could cause problems. You have different changes in the pore pressure in the cement, both for oil and gas and geothermal wells, and changes in the tubular properties as it expands and contracts, and tubular creep. Okay, I want to get through this. OPC alternatives. Is Portland cement the only thing available in the industry today? The answer is no. There are other materials being developed that have been developed that are available now and that are also being developed by some of our research labs and independent people around the world, actually. So we're looking at calcium phosphate cement. I've been involved in placing several jobs with this. It's good to 1,000 degrees F or 500 degrees Celsius. It's resistant to at least carbonic acid, maybe not some of the stronger acids. So there's advantages there. There's other new cements. Brookhaven National Lab is developing a material called thermal shock resistant cement, and I'll show some results of that. There are other materials, geopolymers, etc. I'm not here to do commercial. I'm just mentioning some of the things that are available and that are in the process of being developed. And I think there's going to be some papers later today talking about some new things. So stay tuned. Yeah, some of these materials have improved mechanical properties. Some of them are shock resistant. Some of them are self-healing. There's a variety of materials out there. I'll just leave it at that. So conclusions. There are several significant challenges associated with high temperature, high pressure well cementing. Chemical, thermal, and mechanical durability each have to be looked at and evaluated separately. Placement, we've talked about it before. We have to get the cement in place in order for it to do its job. Testing and thermal modeling, we need to make sure that we properly test it in the cement, that we give your service companies good information so that they can give you good test results. Cyclic stress failure in certain situations may be an issue and needs to be evaluated independently. New cement systems are being developed. They're more durable. They're more heat. They can be used at higher temperatures as we push the envelope higher and higher. And they're more thermally resistant than ordinary Portland cement. Major point of this talk, technologies exist to address most of HPHT cementing challenges. They're there. The challenge is making sure everyone in a given project in a given organization are aware of these and of the cost benefit ratio or analysis done on each one of them. It may be cheaper to ignore a particular solution, but what is the cost of a cement failure? What's the cost of a collapsed casing? What's the cost of losing this well within a year of placement? I can tell you it's very, very high. So technologies exist. You need to avail yourself of those technologies. If you don't know what there are, you need to call someone and ask them for some help. There's lots of people in this room today and around the industry that can help us. The cost of poor cement job is usually really, really high. And that needs to be stressed and brought to the fore with operators that are doing geothermal projects. Recommendations, I guess I just said it. Do proper cement testing, do thermal modeling always, do displacement modeling always, and do cement durability modeling as needed. New cement systems are available, and cementing program decisions should be made based not only on immediate economic costs, but on the economic impact of a poorly designed and executed cement job. That's all I have for this morning. Are there any questions?
So I think okay, so I think that I'll start off, Daniel, and then we'll turn it over to the audience. We have time for a few questions before we move on to the next speaker. So my question, Daniel, is, I mean, a lot of folks here are from the oil and gas industry. What's the difference in cementing procedures and durability and so forth, and the kinds of failures we see in, say, a high temperature oil and gas well, particularly, say, a steam injection well versus designing for a geothermal well?
Yeah. So one of the big failures is not getting cement to surface and then thinking we can just do a top out job. So if you have fluid trapped behind casing, this is real basic, but if you have fluid trapped behind casing and you go from 80 degrees to 500 degrees, not the steam pressure, but the thermal expansion of the water will collapse your pipe. And you'll either lose the well or have to do a major workover. So that's one major area where you can stumble when you're kind of switching from one field to the next. Another area is, hey, we'll just throw the retarder in the, I've seen this before, we'll throw the retarder in the dry blend and road it out to the site. And then it turns out they had to circulate all weekend because they didn't have a float come in from who knows where, and the well is 50 degrees cooler than you expected. Well, you've already got the retarder blended, so guess what you pumped? So a minor thing, for some situations, it may be good to have the retarders in the mixed water. The big thing is you have to have the cement to surface. And the most critical part is, as I'm being repetitive, but the most critical part in a geothermal well is not at the bottom, although you do need a good shoot test, but it's typically the upper zones, getting good cement all the way back to surface and ensuring that you take the steps to do it. You cannot just, oh, we'll just do a top out job. That you can do a top out job, but it's going to be different than you do it in oil and gas. So it maybe covers a couple of the aspects. Yeah. In mechanical failure, there's typically a lot more thermal stress failure, cyclic load on cements and geothermal wells than there is in oil and gas, period. Other questions?
Daniel, one question. Thanks for your presentation. I was drawn from the title of your presentation as directing us towards solutions for the 21st century, right? And that made me think about digital solutions, smart techniques, things like that. What kind of either data science or AI driven type solutions might you see employed in geothermal operations now, or would you like to see?
So I'm actually involved in a project where we're trying to gather data from wells that have been drilled around the world and try and actually learn from that. The big challenge in geothermal, and this has been brought up before, is you're not drilling 100 wells in a field, you're drilling 5. So and maybe they're drilled 3 years apart. So you don't have the benefit of the consecutive learnings. So if we could capture the corporate learnings from around the world and distill some learnings from that and apply it to geothermal, I think that could be beneficial. And that there is a project ongoing where we're working on that, and there more needs to be done. This is just the first step.
Very good. Thank you.
Hi, Joseph Aristides from Weldtech. Have a question. Since I started working with geothermal wells, there's a lot of, in Mexico at least, there's a lot of 2-stage cementing or even 3-stage cementing jobs. Mm-hmm. And you were mentioning that a lot of times doing a reverse circulating will help prevent losses. So is the stage cementing jobs common still in geothermal, or is it good practice, or is something that it has become old and we're looking at different techniques?
Those are 2 questions. So it's probably done. I'm going to let some others answer it because they're more familiar with how often it is. I get nervous when you do a 2-stage job, and other people have done lots of them. So that's probably more personal preference and opinion. I'm a bit more negative. I like to get the entire job done in 1 stage because I think that's cleaner and safer. But there are advantages to 2-stage jobs. And Bill, maybe you can comment on that. And I know Lou could comment as well.
I'm of the same opinion of Daniel. I've had too many failures in stage callers to make me comfortable with them, period. But I think that Mark has a lot better experience with them than I do.
I've seen wells actually completely fail because there's fluids left around the stage collar that are in pipe. And for some reason, they were either contaminated or diluted or never set. And when the well was put on in production, the well failed. So I would rather do, and you can do reverse circulation. It is really not hard. It's actually often better. So people just have never heard of it or never tried it. So they're waiting for Mikey to try it first. And, you know, I can give you a paper that's got 25 case histories if you need some someone to show your bosses that, hey, maybe this might work better.
Okay, thank you all. In the interest of time, I think we're just going to move on to the next, and I'm sure we can carry on this conversation throughout the session. Thank you, Daniel.
Thank you. Nope. Is this mine? Can I remove that? I think that's mine.
So our next speaker is Caitlin Teodoro, and we're going to hear from him about its casing cement bonding, the key for geothermal well integrity. And I'll let Caitlin introduce himself.
Is the one with GRC Teodoro. No. Good. Okay. Thank you. Hello, everyone. My name is Catherine Teodoro. I'm with the University of Oklahoma, and I do research mainly on well integrity, drilling vibrations, and probably another 10 topics, which I don't think I have time to say all of them to you. But one of the things I have, organized my research is that I do believe in modeling, but I trust when I verify the modeling. And I do a lot of experimental stuff. And for those of you who knows me better, I like breaking stuff a lot. And you will see some of the stuff I'm breaking here. And in the today talk, I would like to speak a little bit more details about probably the most interesting aspect of all wells, in particular geothermal, and that's to look at the system, which is the casing and cement, because often we are trying to separate the casing from the cement, and we select the best casing and the worst cement. Believe me, that will never work. And if you do the vice versa, it will never work either. So the idea here is we are looking on casing cement interaction, and this interaction, the way I will try to define it, is about bonding and how they stick together. I will have three parts of this. I will talk first about some experiments. Some of you may have seen this already in the GRC in a different direction, but I will show you some of this. Then I will move to some data interpretation and the results. And obviously, I will conclude this presentation. We do have a very interesting way to see the well integrity. And actually, as Luis have asked all of you, and I will collect the papers, please try to write down what is your view of the well integrity and the way forward for that. And typically well integrity is defined as NORSOC with the application of technical, operational, and organizational solutions. We all try to follow that. We all try to do this. The only problem we have is that none of the standards are telling you what type of cement to use, what type of casing to use, and how you should use these components to solve the problem. They just give you very general, indications. And we all know that if a well fails, we do have a lot of problem. The worst of all is when we lose human lives, but also we lose equipment, we lose the hydrocarbon reserves, or you lose the geothermal well. And not to forget, environmental aspects are as big in geothermal as in oil and gas, because you never want to have all that brine flowing somewhere. And we have some experience actually on that. It has been already said by Daniel a lot about why we need cement and why cement integrity. So probably this is a slide that I will have not to go too much through, but cement job is critical in well integrity. If you fail to do the cement job properly, you already failed the well integrity. If not now, it will happen later. So planning and proper selection of cement is the key part on that. But the biggest challenge on cement is that, in my opinion, cement is the least investigated element we put in a well, because we always do on cement short-term tests, like 1 day, 3 days. If you are lucky, probably 21 days on the cement. And then you expect that your well will last 25 years. So it's a big discrepancy on that. And we have started here to look at how cement casing and formation will stay together. And you will find a lot of papers on that. Very specific is that, the thermal movement, the fact that the well comes in compression and then will move back in tension, creating a lot of relative motion between cement and the casing, and between the cement and the formation, which actually cement was never designed for that. And probably the most key element of every geothermal well is fatigue. If you look in API, the very first API came on the market, they never even thought about the casing or the cement to suffer fatigue. They were just designed for static loads. And now yet in geothermal, almost every load we do is a dynamic load. And because of that, we have to focus a little bit more on this. The next is, if you look at the cement casing interaction, is that we have two totally incompatible systems. You have cement, which is, like a rock form, and then you have the casing, which is a metallic form. Their interaction doesn't really happen by, mixing them together or somehow. The only interaction we have is at the interface between the casing and cement. And that interface is actually very, very complex. I mean, you may say it's a metallic surface, yes, but depends on how much fluid, what type of fluid you put in the well, that interface will change. A lot of work has been done on this type of bonding. And one of the problem I have noticed, and I'm trying now to kind of, repeat this over and over again, is the true definition of shear bonding, because a lot of people are talking actually about cement debonding, but they don't tell you whether that's debonding happens in tension, in shear, or other elements. And therefore, being an academic, I will try to bring you now to some definition. We're going to ask you the definition tomorrow. We're going to have an exam on that. So we talk about interfacial shear bonding strength first, because it happens in shear. But then we have to talk about interfacial bonding tensile strength, which is the total opposite direction, is perpendicular to that. But also, if you look here on this figure, you will notice that couplings are bigger than the casing itself. So therefore, when they try to move, they will actually try to shear the cement. So that will be a pure shear strength of the cement, which is probably a property you'll never get it from most of the cement companies, unless you go to civil engineering in buildings. Shear strength of cement is actually one of the most important property that they will try to do. And inevitably, what we all do is we look at UCS. UCS is the one that tells you whether your cement is stronger, harder, softer, whatever. It doesn't tell you actually too much, but is at least the minimum that we are looking at. Now, the casing and cement interaction happens on the casing body and happens on the coupling. And these two interactions are totally different from one to each other. The casing body, we have the cement sticking to the casing, so that will be the interfacial type of debonding, whether is in tension or is in shear. And then on the coupling itself, there will be a little bit of shear bonding, because the coupling has a certain length. But the most important is actually when the coupling tries to move and is actually trying to shear the cement and then to penetrate into the cement. Two things that are very important. To do so, I have started since about 2015, when I joined Oklahoma University, to look at actually how can we quantify, in a relatively simple method, this bonding performance, and how can we correlate the bonding properties, interfacial bonding properties, shear properties with the UCS, and whether we can create some at least correlations that the modelers can be able to use this. We've done some tests, and today I'm showing you some tests that have been done at room temperature and elevated temperature, only 65 degrees, but we have done a lot of tests up to 85 degrees right now in the lab. All of them, they are actually showing almost the same direction on this. And for this, we have tried to use a push out method, where the cement will be pushed out from a metallic enclosure, which will represent what we like to call the casing bonding. And then we have another setup where we are doing the shear of the cement. And I will show you in the next slides also how the setup really looks like. But I have published that, so it's available all over. What we have noticed, however, on all of our tests is that actually depending on how long the cement cures, we'll have different behavior of this force to push the cement. Please look at this figure here on the right. You can notice it's a pretty nice, smooth, push out. The force doesn't change much. You will see a little bit up and down, but this is mainly from the setup, which is a manual, pump that is doing that. But please look at this one. This was a 3-day, the cement already bond or had time to bond enough. We have actually a lot of debonding, jumping down, and then a kind of rebonding and jumping down again. So the process has been done, shows that actually once the cement hardens a lot, the debonding process is much brutal. And this is very important actually for the long-term evaluation of the well integrity. I have published some years ago, actually last year, a paper about debonding. If you are interested, we can talk in a separate session about that. And here is what I told you. This is the push-out model. We have, the cement inside of this pipe. I prefer to use the cement inside of the pipe because it gives you some simplification in the experimental modeling versus the mathematical modeling on that. And then you can notice here, this is my shear testing cell where the cement will be pushed out here, and this is the line where the cement will be sheared. And I will show you some of the results we have from here. So first of all, the bonding strength, we have noticed that actually bonding strength has a tendency, to increase, for very short time, and after that will kind of flatten. And we observed this not only on these data sets, these were done, and you'll notice here relatively high bonding strength measured, but the reason for that is that our pipes were very rough. We used here brand new pipes with no control of the roughness. Right now we are moving to much more roughness control on this. And very interesting is that actually everything we do in this bonding is that bonding happens within the 3-4 days. After that is having just a flattening effect, which is not the same as we noticed in, for example, the shear strength, where the shear strength has a continuous increase, and up to, typically is accepted that a lot of cements will start still developing strength and especially in UCS and lowering their permeability and porosity up to 180 to 200 days. And that was something that we have noticed here as well. Furthermore, the unconfined compressive strength, there was no surprise here. We have seen the standard, development and distribution. So I don't have anything to talk about here, but we use the unconfined compressive strength to basically have a reference value for every other property and to see whether we can create some correlations. And I will show you some of them coming here. So if you look at this graph, you will notice that actually my UCS is developing, going up and still continuing to develop. There will be, a very short increase later and nothing will happen furthermore. But you can notice that we have the same for the shear and for the bonding. Bonding being the lowest value of all of these. Now, with such low value for shear bonding, now comes actually my title of this, is bonding actually critical for these geothermal wells? Because we know bonding is what has been discussed, the reason why the casing stays in place. Now, if the bonding is not strong enough and the bonding can move up or the casing can move, then how can we do on this? Also, we have noticed that at elevated temperature, bonding of neat cement is lower than bonding at room temperature. We have noticed by, the paper I presented 2 days ago have shown that by adding some additives will actually help you to improve bonding in the short term, but not necessarily in the long term. So we have noticed that this is, after we've done 3,000 experiments on that, we have noticed that actually we have a decrease of bonding at elevated temperature. And that's very important for geothermal to understand that debonding or bonding strength will decrease at elevated temperature. There are a few papers which are trying to argue on that. I'm working actually on a comparison paper on that, but all other papers I've noticed will show the same unless you put additives that are capable to improve this bonding. With this in mind, you can notice here on this graph that shear and UCS correlation is a perfect linear one. And this is something that was expected. Why? Because shear and UCS are pure properties of the cement itself. Has nothing to do with the casing, has only to do with the mechanical properties of the cement. So whenever you change the cement, this correlation will change. But very important is that we have a pretty nice linear correlation, and actually we can use this when we do modeling. By knowing the UCS, you can use this in your modeling pretty easy, pretty simple for that. The challenge comes when we look at bonding. And you can see here on the right side that bonding does not follow anymore a linear equation. It's actually more like a logarithmic one, meaning that actually if you go to a very high strength of cement UCS, the bonding strength actually doesn't increase so spectacular as expected. And that's something very interesting. It means that you will never be able to achieve infinite bonding by just improving the UCS of cement. You have to use additives that will improve the interfacial contact between the cement and whatever pipe you have. Furthermore, all our tests have noticed that the shear strength doesn't really seems to be affected by temperature much, which in a way makes sense, because as long as only the UCS will highly be affected by the temperature, then obviously shear will be affected by the temperature. But since our tests were done, a 65 C, so not a pretty high temperature for a Class A cement, we didn't notice anything on that. However, we definitively noticed a very big change on the interfacial shear bond, actually a massive decrease of that shear bond. And actually, instead of being now a kind of a logarithmic curve, it has a tendency to become a linear tendency for that. We also decided to do some large scale testing. So we use I think 2.5 inch, so 2 3/4 inch tubing to do this testing. And for this large scale, the one you see here, we compare with small scales, and it was published already in the literature that upscaling data on cement may lead to a pretty large variation, which, as you can notice here, from 115 to 4 megapascal in bonding strength is a big jump. But also we noticed that this will be highly affected by the surface properties like roughness, whether it's rusted or not rusted, whether it's covered with something or not. And that was one of the things that we have seen here. And I can tell you that we are now trying to look in more detailed experiments where we are highly controlling, in particular, the roughness of the element. These are some data. I just selected some of the data from the literature just to show you that we have a very wide range on interfacial shear bonding strength. And one of the reasons for that is actually we don't have a standard for this. Every scientist will going to use some of their laboratory options they have, and they will put this. We have a pretty wide range, and one of the reasons I found that the wide range exists is actually because of the pipe used as a bonding element, and of course of the cement recipe. We don't really have reference data. That's why in my lab I started to do really reference data by using knit cement. So we have Class C, Class G, Class H cement. We have also geopolymers used, as pure reference, and then we start adding a lot of additives just to see how they behave on that. Now, to come to my discussion of today, can bonding help geothermal wells? Is that the only parameter of that? I've done here a very simple mathematic calculation. So I consider a 30-feet pipe that will be fully cemented, perfectly cemented, which obviously we know that never happens, but let's assume that we have a perfect cemented pipe, full bonded on all over the section. And I calculate by using, the temperature expansion of the pipe. I calculated the equivalent forces that will exist on the pipe. You can notice on the x-axis we have the temperature, on the y-axis we have the force, and obviously it's a linear equation, nothing fancy on that. But then I plot it on the same chart, the different forces that a value of a given bonding shear strength will exist. So I start with 25. This is one of the low end I also found in the literature, and I went to 145. This is something I found on most of my pipes, which were really rough on the outside. So you can notice here that a low bonding shear coefficient here will allow you to fail your pipe at around 150 Fahrenheit delta, which is pretty low. I mean, we do have that failure. So if you don't pay attention with how the bonding will place, then you will actually fail the pipe. So the casing will start moving around outside of the cement. So there will be full debonding on that. What will happen later? Well, there is another story about what happens in that microannulus that you basically form it here and how that microannulus behave. But you can see here that if you do pay attention and you create cement and also casings with strong bonding properties, so you have a match between the casing coating, for example, and the cement, you will be able to create such good bonding that actually a certain range of delta T will not affect your debonding. So the pipe will stay, as we all want, supported by cement. So pipe is fully supported by cement. But now comes the second question. We know that cementing is never going to be 100%. So you may have actually, instead of 100% full bonding, you have only, I would say, 50%. Well, that is the equivalent of having this value here going down by 50%. And you notice, again, the importance of not only having the proper pipe with cement selection, but also to have a good, job, cementing job done. And then finally, shear. I think the shear will become the new focus on geothermal wells in particular. If you have couplings that will be designed to offer you additional strength in axial motion, so to hold actually the casing inside and not allow a relative motion between the casing and the cement, that could play a critical role in what we call here cement role as a supporting the casing. And shear of cement, has not been investigated in oil and gas. We should try to have more data on this and try to, use this data in a lot of modeling, finite element and so on, to operate with this. With this, I would like to come to my conclusion to say, okay, bonding strength is an important mechanical properties for cement, and actually we should report it. It doesn't matter whether we have an oil and gas or we have a geothermal well. All wells should have this information. We have to have not only bonding for 24 hours, which a lot of people are trying to report now, at least in the academic world, but we need actually long-term properties. We need to see whether the bonding will still be there after 20 days or after 2 months or after 3 months, and whether that bonding will go up and down. We know the classical retrogression of the cement are exposed to high temperature, cement which are not protected for high temperature. We know that exists. We don't really know how the bonding will operate. But also you can see here the shear strength of cement is important. It seems to have a nice linear behavior with the UCS, and that means that will be very easy to be predicted as long as we're going to have a sufficient database to generate this. With this, I would like to thank, first of all, to Tenaris and Central Plains Cement, because they help us to do a lot of testing with materials. Of course, the National Priority Research Program from Qatar, because they have sponsored my students on this project, and my lab, Well Integrity Laboratory at OU. I'm all yours for any questions you have.
I think we have time for a few questions, just a couple though, because we got to keep going. Go ahead. Can you give him the microphone?
Daniel.
On your high temperature bonding test, were the actual destructive tests done at temperature, or was there some cooling that happened?
We have tried both. We did exactly at that temperature, burning our fingers, and we did then by letting this cool down to let's say touching temperature. The results were really not different.
Okay. And then how would you propose standardizing, because you say the surface of your pipe and cement, where that bond occurs is going to greatly affect the bond. Do you have any suggestions if you want to have a universal test done everywhere to how to standardize the surface of that pipe?
Yes, so we are currently working on that. So right now our cells has been, so we are using, stainless steel cells, which are made on a steel with very known control properties. And also we are trying now to use different other materials, like normal carbon steel and other type of pipes, corroded or not corroded and so on. And we try to compare the results and to see what is the range of upscaling on that. So I'm working on this. If this will work, actually, we could use the stainless steel as, let's call it unified bonding strength value. And then we can do some upscaling later based on the roughness. There are some other works that I've read where they were comparing roughness, and it looks like there is a pretty nice relationship between the roughness and the bonding strength.
Hi, Professor Kennedy. So a nice talk. So I have a question. Under which scenarios this pure bonding, debonding thing will happen? Because as we all know, like the length of the well is usually way larger than the diameter. So usually we'll treat it as like 2D, like plane string problem. So under which scenarios those like your experiment will be happens under the, so in the field?
So the debonding happens anytime you are exposing the casing to a temperature difference. So for example, you are cooling the casing because the casing was heated before, or you are heating the casing because the casing was cooled before. Every temperature difference on the casing will impact casing to expand or contract, and that's when the debonding will appear. You just need to reach a certain value of force, overcoming the debonding force in order to be able to do that. Those forces, if you saw in my data for 30 feet casing, looks pretty big, but believe me, it's nothing. By 200 degrees C in a casing, actually, you can reach yield point for most of the casing. Even P110 will be yielded by 200 degrees C delta T.
Okay, thank you very much, Catalin. Appreciate your presentation. Good questions. Okay, I think we will go into our next presentation with Arpita Batija. I'll give you the mic. You can.
Good morning, everybody, and thank you for keeping up till I'm the last one before lunch. So hope I can keep your attention. And I'm Arpita Batija from Aramco Research Center at Houston. So I'm in the drilling research technology team in the cementing group. And my background is actually in geophysics and rock physics. So currently I'm trying to study the different cements that my team members are preparing and testing them, just like Daniel and Kathleen has just pointed out, the interface reactions and how the cement bonds with the formation and the casing. Okay, so I'll be talking about cement to formation shear bond strength evaluation. And my co-author is Roland Martinez from the same place, Aramco Research Center. So this is the outline of my talk. First, I'll give a little background. Then I'll give you the main motivation of this work. Then I'll take you through a quick tour through the sample preparation method, and then show the mechanical properties from the triaxial experiment performed. And finally, the conclusions from the data that I'll show today. So this slide shows the schematic of a well, of an oil well, and the various means of failure. So the light green color shows the cementing in different types of casing, as well as between the formation and the casing as well, and single casing as well. So we can see that the cement can fail in 5 different ways from A to E. And it can be through pre-existing gaps or fractures within the cement, or at the interface between the cement and the formation, or between the cement and the casing. It seems to be moving by its own. And and this can fail through the pre-existing fractures, or new fractures or gaps can also form due to the different scenarios. So I don't think I need to stress more on the fact that cement provides the wellbore integrity. I think we have heard enough throughout this morning, but still I would like to reiterate, because this is the most important part, as to what are the consequences if a cement fails. Now, it can be well-controlled hazard, as all of you know, or it can lead to reduced or no production during the well shut-ins. And all this can lead to expensive remedial jobs and also human losses and environmental concerns. So why does the cement fail at the first place? Because of the stress variations in the near wellbore region. It can also happen during the enhanced oil recovery stages due to thermal shocks, due to stimulation treatments, which can lead to fractures and chemical changes as well. And the casing can also expand or shrink during the shut-ins or when we are recommencing the production. And the variations in the wettability and surface conditions of the casing or the formation because of environmental changes or any of these enhanced recovery treatments can happen. So what is the current state of the art? So the American Petroleum Institute, they recommend that we do the cement compressive strength measurements in a load frame or in a cement analyzer. Now in the load frame, those are unconfined compressive strength measurements, which are done at unconfined conditions. So they do not really mimic the downhole conditions. And the other one is the ultrasonic cement analyzer, which are totally based on correlations of between the cement strength and the sonic transit time. Now, these correlations might not be valid for all the new cement systems that we are coming up with nowadays. So a number of researchers have also done the push-out test, where the cement is set around or on the top or sideways of a cylindrical formation core or a casing. But the problems with that are consistency and repeatability, unless you pay special attention to them. And especially if we have some weakly laminated cores like shales, it's very difficult to repeat the same data and get the same result. So zonal isolation, how does it occur? So zonal isolation is basically protecting the formation fluids from the different zones mixing together. So cement can debond from the interface due to gas migration, channeling, or fracturing within the cement bulk or at the interface. So our method development comes into play when the cement debonds from the formation. So the initial goal of this project was to find an improved technique to study this, how cement bonds with the formation and the cement in the laboratory before we go into the field and put the cement in the annulus and spend millions of dollars into the well. So during the process, we can also evaluate different additives to the cement or the casing treatments because we are in the laboratory setting. And the final goal is, of course, to improve the wellbore integrity by delivering new cement solutions. So our method involves the shear bond strength measurement at the interface with velocity measurements, acoustic emissions, and strains at the downhole reservoir conditions. So therefore, we will not just have a bond strength value, but a qualitative and a quantitative analysis on how the cement actually bonds with the formation. So as I said, I'll take you through a quick tour through the sample preparation method, because this is the most important step and the first step in this method. So we chose 2 sandstone samples to show our method here. So, and they were cut at 60 degrees to the horizontal. And why 60 degrees? Because according to the theory of rock strength, because my background is in rock physics, they say that we require the minimum strength to break a rock when we have a plane at 60 degrees. And then we cured it with class G cement according to the API standards at 180 F and 3000 PSI for 3 days in the curing chamber. So on the left is one of our composite samples with the sandstone on top and the cement at the bottom. And on the right, I've shown our sample wrapped in a copper sleeve with the horizontal and the vertical strain gauges attached and the wires attached to the feed throughs. And it is all ready to be pressurized in the triaxial cell. So in the triaxial cell, we actually put a confining pressure all around it, which simulates the downhole reservoir conditions. And to simulate the overburden stress, we have an actual stress loading at a constant rate of, we used 0.01 megapascals per second. So very slow rate so that we can find out where exactly it fails. So this table is a snapshot of the bond strength values for cement, sandstone, and our composite specimen, which is the cement and the sandstone together. So the first three are the whole core samples. And I have shown the compressive strength values in this. So each of these measurements are from multiple samples. And I have shown only the compressive strength values because in order to find the shear strength, we have to find the correct plane of failure. And this finding the plane of failure can be inaccurate or erroneous in a whole core sample. Whereas in the composite sample, since we are making the plane and it fails along that, and we have verified that it fails along that plane of failure. So I have shown the mean strength, shear strength for those composite samples. So what we get from just the strength values is that the cement strength is much lower than both the sandstone samples, that is Berea and Tori sandstone. And the cement bonds much better with Berea than with cement, than with Tori. As you can see that the shear strength as well as the compressive strength of cement Berea is more than cement Tori. So next, I'll just give the basic principles of the acoustic emission method. So this involves detection of defects using sound or certain frequencies which are used, and they give us an idea about the defect. So the acoustic waves are generated by the transient energy due to microcracking when we take the sample through the stress. And different acoustic emission sensors can be placed on the surface of the sample to define the location of the damage. The different attributes for the acoustic emission method can be rise time, amplitude, the number of counts during a duration, the threshold. Now, multiple attributes can be used, or a single attribute can also give us an information about the defect mechanism happening in the sample while we are taking it to failure. And these acoustic sensors are, they are not active. So they only listen for the sounds. And it's similar to you can refer to it by listening to a tree when it is breaking, and you can listen to the sound, and that is what we are doing in a sample. So we are listening to the sound when it is breaking at a certain frequencies, at those low frequencies. So our methodology, as I said, gave a brief thing that it's a combination of the velocity, the strain measurements, and the acoustic emission counts. And what we have seen is that the deformation history in a rock or a concrete specimen, they can be divided into 5 major regions. So first, what happens is the initial compaction of the specimen. And that is mainly from the pre-existing cracks, which are perpendicular to the principal stress direction. And this region is associated with very low acoustic emission activity and an increase in the primary and secondary wave velocities. So an increase in the primary and secondary wave velocities, they refer to the fact that the sample is actually strengthening because we are closing the microcracks. So the second region is a quasi-linear elastic portion where we have either no change in elastic velocities or very slowly changing velocities. The third region is where the microcracks initiate and extend. And the cracks generally forming are predominantly parallel to the principal compression axis. And we have an increase in the acoustic emission count. And they keep increasing until it reaches the acoustic sensor limit. So it depends from different sensors, what is the limit. And that is where we define that the region 4 has reached where a macrocrack is formed by joining of different microcracks. And this is where the acoustic emission saturates. And from this point on, from the region 4, the primary and the secondary wave velocities, they start decreasing. And that is how we know that the sample is reducing strength. And they start getting weaker. And finally, these any of those microcracks, they combine to form the shear plane of failure on which the sample or the specimen slides and fails. So it's a little easier to understand this with this diagram than with those words. So the main events that happen, as I said, to remember, are written on the top. The first is the compaction event, then the microcrack generation and the macrocrack generation, which are together written as the multi-cracking event, and then the sliding event. The green arrows point to the direction of the axial stress direction. And you can think of it in a real world as the overburden on top of any formation or the cement setup. And on the bottom, I have written the regions. So the compaction event, that refers to the region 1, which is due to the microcracks closure, which are mostly perpendicular to the axis, the axial stress direction. And then the microcrack initiation or the propagation, and which are mostly parallel to the axial stress direction. Then the macrocrack formation by joining of these microcracks in the region 4. And finally, the failure, the frictional sliding along the shear fault, which is formed by the combination, by joining of the macrocracks. So here I show the data in one of our whole core samples, which is the Berea. Again, this is just data from one of our samples. So the 3 dominant events, that is the compaction, number 1, the multi-cracking, number 2 are pointed with the double-headed arrows. And you can see that the pre-existing microcracks give us the compaction event, which is in the region 1. And then the microcracks start initiating or the forming ones, no longer from the pre-existing microcracks. And they finally reach the acoustic sensor limit and form a macrocrack when we call that this is a macrocrack has formed. And they were actually validated by looking at the samples after failure and also before failure. And then after that, the macrocracks join and the sample fails. And on the right, I have shown the primary wave velocities as a function of axial stress. And here we see that, again, where the sample is strengthening during the first region or the compaction event, where the specimen is actually strengthening. And then the velocities decrease as the specimen is becoming weaker. So on the left, these are I have shown the acoustic emission counts over 1,000. And then on the right in red is the axial stress. So we can actually get a lot of information from the velocities, acoustic emission counts, and the strain that is happening in the sample. So this is the failure mechanism in Tori. And we can see that just by looking at the data, it's very different. And the difference is that now we see that the microcracks, the pre-existing microcracks in Tori are of much smaller amplitude, and they are larger in number than in Berea. Also in the region 2, we can see that the number of macrocracks formed in Tori is much larger than in Berea. So we wanted to delve deeper into the structure, internal structure of these rocks. So we took them through the scanning electron microscope. And what we saw is that, what we already know that Berea has a higher porosity and higher permeability than Tori. And in the SEM figures graphs, we see that Berea has much larger grain size particles and Tori has smaller grain size particles. So what is happening is there is a lot of empty space in Berea where the sand grains move and interconnect. And so the stress is getting distributed. Whereas in Tori, it's not able to move, and that's why we have a larger number of macrocracks generated. And so before a few of them join and fail the sample. And this is an insight which is not possible to get just from the bond strength values. So this here I show in the pure cement where we have actually used the class G cement. And in cement, what we see, the difference between a cement specimen, the data in a cement specimen and the rocks, is that we have much lower number of pre-existing microcracks. So the region 1 is much short-lived. And also in the region 2, where the macrocracks are formed, we see that they keep increasing. We can visibly see that they keep increasing in amplitude as we increase the stress. So here in this slide, I have shown the data from one of our composite specimen, which is the cement with Berea. And what we see that in the composite specimen, we see a combination of sandstone behavior as well as cement behavior. That is pre-existing microcracks we see, and also we see the larger number of macrocracks generated. And here in Berea, we almost see a perfect inverted hue, which is because the region 1 and the region 2 are both staying for the same amount of time. Whereas when we look at the cement Tori specimen, we see that the region 1 is long-lived than the region 2, which goes back to the point that Tori has larger number of microcracks, pre-existing microcracks than Berea. So these are the conclusions from this study, that the sample preparation techniques are key to consistent results and accurate predictions because it lowers the number of variables. And a few of the sample preparation techniques that we have, that I would like to point out is keeping the surface roughness, as Kathleen was pointing it out, keeping it constant. So we took our samples, when we cut our samples, we cut it through at the same cutting speed, that is the same rotations per minute, with the same machine, so that doesn't change. We also took them through the optical profiler to look at the surface so that we are not changing the surface roughness. The temperature and the pressure at which we are curing the cement should be kept constant. The length and diameter of the sample of the specimen should be kept constant so that we get consistent results. And also the humidity, and you can also keep them constant, try to keep them constant. The acoustic emission count in conjunction with the velocities and strain measurements, they describe the failure mechanism that is happening in cement formation as well as our composite specimen at the downhole conditions, which mimic the real reservoir conditions. The deformation history of a specimen can be broadly divided into 5 major regions. So the fracture process zone creation from the microcracks leading to the macro cracks, and then the macro cracks joining to form the shear fault, which actually causes the specimen to fail. So although the 3 dominant events, that is the compaction, multi-cracking, and sliding, are visible, or sometimes they might not all be visible, because some of these events might combine together and give us a combined, show us a combined result, or one event might be short-lived than the other one. But still there are basic differences, as I showed you in the data, and the data demonstrates that they relate to the basic structure of the specimen. So for example, Tori has larger number of pre-existing microcracks than Berea, although they have very similar compressive strengths. So just the compressive strength or the UCS values would not have given us this information. And Berea has more empty space because of higher permeability and porosity. So it can distribute the stress much better, and hence we have much smaller number of macro cracks in Berea than Tori. The compressive bond strength of cement Berea is more than any of its constituents, which is the cement and the Berea. The shear bond strength of cement to Berea is more than cement to Tori, and this might be related to the higher permeability, which allows the cement to go and fill into the pores, connected pores of the Berea, and give it a better bond strength. So I would like to acknowledge Peter Bull and Carl Themlitz for all the fruitful discussions during the execution of this project. And I would like to also thank the management at Aramco for allowing me to publish this and present it in front of you, the drilling team colleagues for all the help. And I cannot go without mentioning the IT and HR support for the daily help. And finally, thank you for giving me the opportunity to present in front of you after a long Corona break. And I would appreciate any questions and would be happy to learn from you and also ask any questions, discuss.
Thank you, Arpita. I think we have time for one question before we can break for lunch.
Thank you. I've been under the, I think, misguided impression forever that the failure in cement is due to the lack of tensile strength in cement. But from what you presented, it looked to me like the cement fails first in compression. Is that what you feel? That it fails in compression rather than tension?
So
where the cracks form, I'm sorry.
So the study that I have shown, we are studying the effect of the compression, the compressive strength. So we are not applying the stress in the in tensile condition, but tensile failure is much higher than the compressive strengths.
Right. So then to prevent a compressive failure in the cement, you need a cement that builds compressive strength greater than the stress it's going to be exposed to?
Yes. And also, like the main point of my of this method that I have shown is actually to study the shear strength. So that's not even the compressive strength. So shear strength, I defined the shear strength. I know Kathleen also went through it. So is when you're applying the compressive strength, and if you know where it's the plane of failure, if you know that, or where it slides, then you can find the correct shear strength.
So you're measuring this in confined or unconfined?
Confined.
We need stronger cement.
Okay, I think it's time for us to, they're serving, getting ready to serve lunch on site. And I think we all can agree that the first presentation, the speakers were just outstanding and we really enjoyed it. And we're looking forward for the rest of the time as well. So we're taking a break right now. It's supposed to be an hour. We're a little bit late, about 5-10 minutes late, but we'd like to rejoin back in an hour back here in this room. So lunch is being served. Thanks.
Thank you.
Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Allen S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that geothermal rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep dive-infused geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled at a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Alan S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognised this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that geothermal rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep tariff-based geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled at a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and inclusion to provide a brighter future for Earth and all its inhabitants. Our organization and community embrace and celebrate our members' differences. It is a responsibility of Geothermal Rising to encourage and promote diversity, equity, and inclusion. As a global geothermal nonprofit organization, we are committed to connecting the geothermal community. There is more work to be done, and as we expand across markets and internationally, Geothermal Rising will continue to seek equitable improvement to elevate the geothermal community.
The infrastructure investments that are in President Biden's Build Back Better agenda are going to turbocharge geothermal energy in America. We're talking about the biggest investment in clean energy and transmission in history. So my message to you is this: when it comes to geothermal, America is open for business. We are so ready to partner with you to get this done. We are grateful for your tireless work to elevate this important, clean, and reliable energy source. And we're grateful for your willingness to train the next generation of geothermal professionals. And we are excited to secure policy wins all across the country. So thank you so much for inviting me to participate. I hope you have a fantastic conference. Our Geothermal Technologies Office has been investing in developing and deploying geothermal for decades. And we've asked Congress for $57 million more for this program in the upcoming year.
This is the Alan S. King coal-fired power station. It produces 600 megawatts of steady, reliable baseload power. Shutting down this power station is the right thing to do, as we've got to stop burning fossil fuels and save our Earth. The problem is, we can't replace this power with just wind and solar. In California, the Public Utilities Commission has finally and formally recognized this problem and has now called for 1,100 megawatts of firm and renewable 24/7 electricity generation by 2026. That's geothermal energy.
We're learning from both successes at the state level, like last year's California Public Utilities Commission procurement decision that geothermal rising helped to boost. And we're learning from our international work, obviously, like Europe's progress on district heating systems. In April, we announced $15 million for geothermal research projects in West Virginia as part of our investments in job creation and economic opportunities in the hard-hit coal and power plant communities area.
WVU Morgantown campus has been identified as a priority location for deep tariff-based geothermal project. Therefore, to perform a geothermal resource quantification and risk assessment, an exploratory well will be drilled to a depth of 15,000 feet, along with a full logging and coring program. We'll be using state-of-the-art drilling technologies for this exploratory well. The project will have implications beyond West Virginia University campus. It will provide data for geothermal resources for other potential sites in the Middle Appalachian Basin that has similar geology and demonstrate geothermal energy is a national resource but not limited to Western states.
Department of Energy sees geothermal as a crucial tool to help us tackle the climate crisis, to deliver 40% of the benefits of clean energy to disadvantaged communities, and to build a skilled, diverse energy workforce.
The newly formed Diversity, Equity, and Inclusion Task Force has been very busy since we formed 7 months ago. Our first goal was to create a DEI statement that shows Geothermal Rising's commitment to improving diversity, equity, and inclusion across the geothermal community. Geothermal Rising is committed to improving diversity, equity, and
Hello, hello. We'll go ahead and get everybody in here, get going after lunch. Hopefully you had some coffee. And we'll get, hopefully not too tired after that great lunch. This session here is going to be over some slurry designs, right? So at the end of the day, we talked a lot about cementing. We had a great presentation in the morning, just kind of talked about, the basics on getting cement around pipe. And once you've done all these things, then you got it in place, slurry design really comes into place. How are you going to get it placed in high temp environments? How are you going to get it to perform and improve that shear bond that they talked about this morning? How you're going to improve the properties for high temperature placement? These are all important aspects of slurry designing in geothermal wells. And there's a lot of good presentations on some new materials and some case studies that will be going in. Do you have anything yet?
Nope, I think you touched on everything that's on here.
Okay. All right, so we'll go ahead and introduce our first speaker. It's gonna be Nicholas Droger. He is one of the sustaining leads at Schlumberger, and with that, take it away.
Thank you, Jeff. Yeah, I will. Today, I'm going to do a quick review of some case studies that we have pumped, and I would like to acknowledge my co-author Nicolas Flamand, who is in France and couldn't join us today. Nicolas Flamand is leading the software and the modeling team. So you will see that I will spend some time first briefly going through geothermal conditions, but everybody here knows about them. Then I'm going to explain how we can use modeling to predict what conditions can happen downhole. How do we design special cement for those high temperature conditions, and then go to those case studies. So everybody knows those geothermal conditions. We have temperature and pressure fluctuations downhole that can first create some phase transitions in the cement, and then also create some stresses and in the cement thieves that lead to risks of failure in compression and in traction, as well as risk of some microannulus. How can we try to prevent those? We can try to prevent those by first trying to understand and predict what conditions are going to happen downhole. And you can start by predicting what's happening even when you start with the drilling, when you start by having fluid running down your well and going up the annulus. So you can predict the fluids. You can predict the fluid conditions. Then there is the step of cement hydration that you can predict, and the mechanical properties of the cement with these temperature and pressure conditions. And finally, during the life of the well, it's important to know how the cement is going to behave and if there is a risk of failure. So the simulators and the models are here to help design the job. If you know in advance what's going to happen downhole, you can better prepare your fluid and design it accordingly. I know this has already been touched earlier this morning, but I want to start with the first step. Having a good cement placement is the first step to achieve a successful cement job. And for that, you need to know the properties of your fluids in the temperature that happen downhole. So again, here we reach the question of, do we have the equipment necessary to measure the fluid properties at high temperature? And this can be quite a challenge when you reach extremely high temperature. How do we model the rheology, for example, of a cement at 200 Celsius? That's just something. Do you take the measurement at the temperature you can reach and then extrapolate? That does not necessarily work. Here on the graph, what you see is the model of displacement of the fluids during a cement job to see if there is any risk of having mud left on the wall. And by running this simulation, you can better understand what are the properties of the fluid you need to adjust to reach no mud on the wall. So you have placed your cement, and we assume that the placement is good. But now, how is the cement going to behave mechanically with changes of pressure and temperature in the well? You know that stresses are going to be generated. What model can we use to predict that? And you see there are several models here on the slide: thermoelastic, thermoporoelastic, and thermoporoelastoplastic. And the more complex the model, the more computing power you need to be able to resolve those models, and the higher quality the input parameters you need to get good output. So we need to find a trade-off between using a simple model that is less sensitive to the input parameters. If you have a simpler model, but with input data that is not entirely correct, but still gives you a good output, that's preferable to a very complex model that requires extremely fine input parameters, such as formation, mechanical properties that are not always easy to get, fluid properties at temperature that might not be easy to get at this extremely high temperature, as I mentioned earlier. So today, at least in the current model we're using, we are actually using the first one, this thermoelastic, and using this thermoelastic in a pretty simple geometric allows us to have a very robust model that does not depend too much on the input parameters. So how do we, what's the workflow to go from our input parameters to our stresses? First, you need to have a space discretization. You need to decide how you're going to break out your well, and we do that in a one dimension. Time discretization is also important. You need to be able to predict the stresses in your well for a long period of time. So you want to be very precise at the beginning when the cement just starts setting, and then go on for maybe 5, 10, 15 years. And we heard that we want geothermal wells here even for more than 30 years. So we need to be able to have a simulation that runs for multiple years. Temperature here in our model, we just choose a simple diffusion equations. We don't take into account that cement reaction will heat up and so on and so on. We just use simple diffusive equations. As well as for stress, we resolve the stress using the Lamy equation, and the failure analysis using the Moore-Coulomb, exactly like was presented earlier. So the beauty of using a simple model here is you can actually input in the model several interfaces between the several casings, several cement sheaths, up to 9 different interfaces can be input in this model. Okay, so now we have our stress. We know how the cement is going to behave, but what's important in our high temperature wells is to design a cement that's going to not fail. And the challenge, there are different challenges with the high temperature. One of the main ones that we identify is the thermal expansion coefficient of the steel that is high, and the usual thermal coefficient of the cement that is low. So how do we address some of those challenges of designing cement, not going away from ordinary Portland cement at the moment? We still use ordinary Portland cement. For the thermal stability, we typically, as everybody, use 35% of silica. That allows us to form this turbomerite and then axonotite. As you can see on the graph on the right, it's an XRD of a cement that was aged 1 month at 344 Celsius, and all the peaks relative to axonotite show very well. As for the thermal expansion, we want to have a coefficient of thermal expansion of our cement as close as possible to the steel. So we are going to use some additive in our cement that's going to increase the thermal, the coefficient of thermal expansion. And ideally, in terms of mechanical properties, we would like a low Young's modulus so that the cement is going to be more flexible and more easier to adapt to stresses. And despite having a low Young's modulus, we want to keep a high compressive and tensile strength to prevent any failure. Looking at the thermal expansion, conventional cement is between 9 and 10 to the -6, where with the new system, we managed to increase it by 1.5-fold. And if you look at those two graphs, the one on the left is compressive strength and the one on the right, tensile strength. It is the stress generated inside a cement when you have a temperature increase from 10 to 250 Celsius in 3 days. And what you can see is that by increasing the cement coefficient of thermal expansion, you definitely decrease the stresses generated inside the cement. And more importantly, if you compare the dashed line, which is a high Young's modulus cement, to the solid line, which is a low Young's modulus cement, you see my point about designing a cement with a lower Young's modulus that's going to have much lower stresses generated by this temperature increase. Going from the thermal properties to the mechanical properties of a cement when it's exposed to a high temperature, I just need to spend a little bit of time on this slide. What you have here is the tensile strengths as a function of the Young's modulus for different systems, being conventional or being this new resilient cement. And using the model I explained earlier, we determine at which tensile and Young's modulus the cement is going to fail. So the red line and the green lines here show the conditions in which the cement will start to fail. On the left of those lines, the cement is good. On the right, if the cement gets into those stresses, the cement will fail. So for conventional systems, you can see on the left, oh, sorry, I needed to, sorry, here, maybe it's easier if you have the legend. So you have the initial, I don't have a pointer, do I? No. Yes, okay. Yeah, okay. So for conventional cement here, you can see that the initial mechanical properties and the mechanical properties after 1 month are both in the cement failure. So if you use conventional cement in these conditions of 6 days heating to 350 C, the cement is going to fail. If you use a little more complex system, but still conventional of a thixotropic cement, you can have a cement that is not going to fail initially, but after 6 days heating, it's going to be into the failure system, into the failure zone. On the contrary, our heat or steam resilient system, depending on the initial or even after 1 month at 344 Celsius, they are both in the zone where the cement keeps its integrity. And those two curves, the green one is simulating a fast heat up 2 days to 350, and even if you heat fast, the cement is still going to be to be good. Yeah, so we have managed to design a cement using conventional Portland cement that will not fail under those thermal stresses. And I have two case studies, one in Indonesia. I will not read all those conditions. You can read that it's a steam injection well. So most of this work, by the way, was done for SAGD and steam injection, but they can easily be used for geothermal wells. We heard the differences this morning, but the material can be used for both. I just want to mention here that we definitely use a low Young's modulus cement compared to conventional, and that no remedial work was necessary on this well for more than 2 years after it was in production. We're still far from the 30 years, but 2 years is already a very good case study. So just to show you how we used our modeling, with the input parameters of temperature, we can model the stresses inside the cement. So you have the casing here in blue, the cement is gray, and the formation in brown. And we have here the compression, the compressive strengths, and in green, that's the failure zone. So every time the compressive strength reaches this green zone, it's in failure mode. So the cement is going to fail in compression. Whereas with the new resilient system, we are never reaching any green. The scales are not exactly the same. Obviously, here we're going to, here it's minus 5,000 PSI, or here it's minus 700. So the stresses generated inside the cement are really much lower than in a conventional. And same in traction, the conventional cement will fail in traction, while the new resilient system will keeps its integrity and doesn't fail in traction. You have all the references of this work that was published if you want more information. And going to the second case study, again, a steam injection well in Canada, in Alberta. In this one, we aged our special cement that has this HT resistant feeder for 6 months, and looked at it under an SEM, and you can see, or maybe not because the resolution is not that good, the high temperature resistant feeder that provides this high thermal coefficient keeps its integrity. It doesn't disintegrate, doesn't change shape, is not affected by 6 months at 344 Celsius. Similarly, you will see that the compressive strength doesn't change within 6 months. The tensile strength doesn't change with 6 months, and the Young's modulus. So we have a system that is stable for 6 months. This system was 6 months in a curing chamber at 344, and the properties didn't change. That's just to show you that we managed to have well integrity. You have a log here, and there are actually two logs done on the same well. The log on the left is done with pressure inside the casing, and the log on the right without pressure. So as you go deep, you can see that yes, there may be some microannulus deep in the well, because you see this blue when it's not pressurized, whereas it gets dark when it's pressurized. So the casing is pushing against the cement. But to go to the point that we have many very good sections that show that integrity between this section and upper sections is guaranteed by those very good sections, and it seems that we do have good cement up to the surface, which I understood is key for geothermal wells. With that, I will conclude saying that it's important to understand and define and understand what are going to be the conditions in your well, and for that you can use some models. The most difficult thing to use models is to have the right parameters in. It's garbage in, garbage out. If you don't have the right parameters in, you will have a number out, but it will not provide you any good information. This has been applied mainly to steam injection wells, where we have designed thermally resistant flexible cement. And I showed you two cases, one in Indonesia and one in Alberta. I'm open for questions. Thank you for your attention.
I have a comment and a question. I thought it was very interesting that you showed a variation in the durability of the cement depending on the heat up rate. I know several operators are going to special protocols that they will heat up their wells and cool them down much slower rate. And I would encourage you to say more about that, because I think that would be very important and very useful.
No, yeah, definitely you can see it here on this curve that if you heat up faster, the failure zone, which is here on the right of my graph, is much bigger than if you heat slowly. So going from 2 days to 6 days, yeah, there is a value, there is a money involved in waiting 4 days. But yeah. If your cement ends up failing, we are going back to the remedial, which is much more expensive.
Yeah. Well, I would encourage you to bang that gong more and let people know about the significance, even write a paper about it. I mean, that whole subject, I think, is worthy of discussion, my personal opinion. And then a question, very interesting that you're able to adjust the thermal expansion of the cement. Is that limited to one specified density, or do you think you can get that over a normal density range that are used in wells?
No, it's pretty wide. We can adjust the density of the cement system. Now I know you all here are interested in low density, and that might be more challenging because to go to lower density, we use feeders that will probably decrease this thermal. So, that's the oil and gas versus geothermal. Yeah. So there might be more study to do to go to extremely low density, and that's a good point you have here.
Hi, Nicholas. Very interesting work. So may I know, when you do your thermal simulations, what kind of boundary conditions you are using for your simulations? Is first, second, or mixed?
Oh, I will have to use a. I will have to answer later because all the modeling work was done by Nicolas.
Oh, okay. I'm just curious.
Yeah, I will get back to you.
Okay, thank you.
Using high density cement in these steam injection wells, and are you cementing the casing back to surface?
In those cases, yes.
And what placement method did you use for high density cement? Conventional circulation, reverse circulation?
Yes, I believe conventional.
Thank you.
Yep.
Time that we have for questions. Thank you very much.
Thank you.
So the next speaker will be talking about hexagonal boron nitride reinforcement for multifunctional well cement. And I'd like to introduce to you Ruzbe Shahsavari.
Right. Good afternoon, everyone. It's a pleasure to be here, and I thank the organizers for putting together this interesting workshop. So my name is Ruzbe Shahsavari. I'm the founder and president of Secret Technologies, an invention and technology company developing new formulations for cement, including nuclear application where there is radiation, high heat, and corrosions, or special construction projects where there is a demanding conditions for cement, and also oil and gas. So what I'm going to describe today is a multifunctional well cement. I slightly changed the title to make it more understandable, that what we are developing is actually a cement that does multiple function only with one additive, and that includes high thermal conductivity, high compressive strength, tensile strength, better rheology, and compared to other technologies that you need a lot of additives for each single of these properties, what we are developing, or what we are basically proposing, is that there are ways you can leverage nanotechnology and change the microstructure of the common cement like class H and class G and still get some favorable properties as opposed to adding too many additives. So I guess previous speakers did a good job on the importance of well cement and its function, so I don't want to go through this. But if cement fails, as you know, there are costly remedial jobs. It may halt the productions and limit further development opportunities for the stakeholders and other impacts. So if you look at what is exactly happening on these extreme conditions, is that I borrowed this plot from Stomejer, but when you increase the temperature, what happens is that at around 110 degrees or so, there is a series of phase transformation starting from 110 degrees and above. For example, tobermite 11 angstrom turns out to be like 9 angstrom, so it a bit shrinks, and then that shrinkage leads to some porosity. Porosity may invite some further fluid inside, and then that may reach the steel casing and corrode it. And then when you increase the pressure alone, there is early hydration or microchannel formations. But now you combine high temperature and high pressure, it's actually not that quite intuitive. So there is a complex phenomenon that's happening. So it depends on the conditions, but it's very complex. In geothermal wells, there might be even other extreme conditions like corrosions or carbonation, because there is hypersaline water, or there is high CO2 concentrations, and also high H2S that may all exacerbate the situation. So there are different products developed in the market to address extreme condition. I just put some names here, like Thermalike, maybe mostly using for geothermals or others. Not certifying or criticizing any of the products, but what is common between these products or maybe others? They are usually based on first of all, they have high costs, and cost is very important in this low margins markets. High cost or scarcity of the additives, and then they are developed based on trial and error. So if they say something fails, they add another additive, and then if some other property is compromised, they add another additive. For example, in Thermalike, because they wanted to increase the retardation, they add citric acid, but then strength must be compromised, so they add fibers to reinforce it in terms of the strength. So there are lots of additives added to reach some good functionality. And eventually, there is also questions about failure rates, because downhole is very difficult to really assess what cement was the really good cement. So with this, you may guess what is at stake: how to develop a reliable and multifunctional well cement that can address multiple conditions at once, meaning high temperature, corrosive conditions, and others. So maybe one strategy would be changing the backbone of well cement, or maybe developing a new, totally different new cement. But based on my understanding, there is nothing on the horizon that can replace cement based on cost. So if you're talking about like class GH cement or Portland cement, there might be some other cementitious material, but they cannot compete with the cost. So the best bet would be just stick with what is the lowest cost, and instead improve its properties to the extent possible and push the limits. For that, we need to start from change the cement crystals or modify the chemical pathways that this cement forms, basically many microstructure. And for that, using some nanoscience and nanotechnology that I'm going to focus on. So it might be buzzword, but all that is just there are more degrees of freedom at smaller scales. And nanoscience, it does not mean just nano, it nano and size dependent. In fact, at below 100 nanometers, it's been shown that several of these materials, they show size dependent properties. So if let's say, thickness of your plates is 10 nanometer versus 20, you get different thermal conductance, different mechanics. So it is size dependent. And then that's what we are actually doing, it to leverage that size dependency to make it compatible with the well cement. So with that tuning, you get several exotic properties. For example, ultra high thermal conductivity, ultra high mechanical strength or electrical conductivity. And the reason is that they are not based on conventional physics. So they are based on quantum physics and quantum mechanics, where the electrons are bonded in one other dimension. So things are extremely small. So they are supposed to bounce back and, in a very simplified way. So they don't follow necessarily conventional physics language. So if you get the history of this nanoscience development, it was first developed at Rice University in 1985, carbon buckyball, where it is all like a molecule that's all carbon, like a sphere, C6C. And then Rice actually got Nobel Prize in 1998 for that discovery. And then that was followed up by carbon nanotubes in 1991 in Japan. It's just a 1D fiber version of that same sphere. And then in 2004, a 2D dimension of it, like graphene, was developed. They also got Nobel Prize. And then that 2D material actually initiated a series of other 2D materials. One of them actually is the main topic of this presentation, is the boron nitride. So as opposed to carbon, it has boron and nitrogen. This is the one that is the kind of blue and pink here. It has boron and nitrogen alternating in the hexagonal shape. And then they are like a strong ionic bond. So it provides some much better properties compared to graphene. For example, in terms of thermal stability, it's twice more stable, or in terms of the hydrophobicity, it is a lot hydrophobic, so it doesn't like water. So some situation that you don't want the water to penetrate your cement, that might be better. And other properties, for example, it is electrically insulating. There are also other nanomaterial being developed, like graphene nanoribbons, where your plates, you can cut it to several ribbons. Now ribbons have more edges on the side, so there is better connection to the matrix, but there is cost involved, or even 3D versions of it. So with that, the problem is all these materials, the cost and scalability. And that's why this actually plugged a lot of commercializations of a lot of nanomaterials. And sometimes toxicity, but to a lesser extent, because these are, it's been shown that they are not actually not toxic as initially proposed. So what we have done over the past few years, I've been working in this materials for the past 10 years or so. We have actually solved the problem of scale and cost for these materials, and some recent publications we did in Nature and others, that they are now being produced in massive scale, these 2D materials. And what was remaining was that how to make it compatible with the cement matrix. And that is what actually my company was focusing, that making materials like fibers, if you add it, you can put in the matrix, but there is not much connections. And then all you get is some reinforcement. So what we are doing is actually use them as a seed point or template, so that cement microstructure is gonna grow on the top of that in a kind of semi-epitaxial way. So you get a better microstructure and better nanostructure. So it is more than just an additive like a fiber. It is acting as a seed point or template to promote the growth of the better microstructure in cement. So this is actually a summary of my properties we have got so far. In fact, this is my favorite slide in this presentation. So you see, it's a host of properties that we explored with this small one single additive we add. So compressive strength and tensile strength, about 20–30% improvement. And we didn't try more. There was room to push it more, but we thought, strength is not a big factor in cement. Cement is already strong, so this is like a bonus given. But thermal conductivity, we got it, for example, 25%, 30% more. Thermal tolerance, the residual strength was 90% more than the control sample at 120 degrees. Rheology, we got like 60 to 40% lower yield stress and lower plastic viscosity. So the importance of this is that you need less pump and less energy send it downhole several kilometers. And electrical conductivity, shrinkage is very important, 50% lower. And that is also, again, goes back to the porosity. If your cement doesn't shrink, you have less porosity, and less porosity durability is increased because there is not much room for the deleterious ions to penetrate. And adhesion strengths we tested, compared to the control more than 100%. Hydrophobicity, like 65% more than control. Again, my control, I mean class H cement. So what we are adding is still class H cement, but with our additive to make it multifunctional. Abrasion resistance, extremely high, and density doesn't change much, around 1 or 2% of the control sample, and corrosion resistance around 20 to 30%. So here, what I would like to emphasize is that in each of these single properties, I can increase the properties even further, but the point is that some of the others may compromise. So we try to find a balance that several properties are maintained in a good range and still cost be minimal. So I'm adding extremely low amount of this additive in the system. And the reason is that these nanomaterials have high surface area. 1 gram of it may do a job of like 20, let's say 1% of it may do a job of 20% of other additives, because high surface area is extremely high. And actually, even if you put 1 gram of it, it fluffs, and then you see, it seems a lot, but when you weigh it, it's actually very low. So the methodology, the methods we used was basically, iterative, a lot of synthesis, characterization, lab testing, and then there's some scale-up and pilot testing we are doing, and some cost-benefit analysis. So here I'm gonna dive into some of the properties. For example, pumpability. With this, higher temperature viscometer to measure the viscosity of the sample. So, I don't want to go through the details of the plots, but basically what we showed was that there is 65% lower yield stress and 40% decrease in plastic viscosity. So that means lower pump force and lower pump energy, going especially for geothermal that you want to send it several kilometers downhole. These are more information on rheology and gel strength. So gel strength, for example, didn't change initially. So that means that early hydration products are not changed in terms of the setting. And then one common thing with a lot of additives is that there might be segregation between your additives and the whole slurry. So what we did is just going through this kind of fan degrees versus RPM, going ramp up and ramp down to make sure that this whole mixture is homogeneous and there is no segregation. So here to see that the one that we developed based on these nanomaterials and class H, the blue one composite, the two plots pretty much overlap, whereas the control sample, there was some segregations between them. And then we did some free fluid tests. Again, after a few hours, there was no change compared to the control. In terms of mechanical properties, this is actually very interesting, is that in this nanomaterial, it's not like the more the better. In fact, there is a sweet spot. If you pass that stage, the properties may decrease and you may basically compromise all you are intended to. So we did a lot of testing to figure out where is that really sweet spot that I get the best mechanical compressive strength and tensile strength. And at the same time, rheology and all of the other properties are in a good shape. And this is actually what we got, like 20, 30% increase in compressive strength and tensile strength. Then we did thermal stability tests. So initially we went to 120 degree and tested the residual strength at 24 hours. So we basically put it in the oven at 120 degree up to 400, and then take this cube, the 2-inch cube back, and then did a strength on it. So you see that residual strength in all of them compared to the control, which is the first column, is significantly higher in different mix design we had. So this is good news for exposure to high temperature, even up to 400. Then we did combine heat and corrosion. So we exposed the sample for a few days in acidic conditions, maybe pH 4 or 5, relatively mild, and then tested it again at 100 degree and 120 degree after 24 hours. So still, as you see, the different mix, the three mixes that we had, they showed around 20-25% better residual strength compared to the control, while they were exposed to both heat and acidic condition at the same time. Then we did some other properties that what I call multifunctional, because now you have interesting like hydrophobicity, thermal conductance, and electrical conductance. For example, for thermal conductance, the plot on the left, what we did was simple tests, measuring thermal conductivity of concrete or cement is relatively special equipment. But one simple test was that quick test. We put it in a hot plate, let's say at 200 degrees, this hot plate here in this plot. And then we measured the temperature on the top surface through a thermocouple. And then the more heat goes up, it means that the more conductance is happening. So with that, with assuming everything linear, we got around 25% increase in the thermal conductivity. Resistivity came down slightly to around, that is because the system was more connected. So it is electrically also more conductive. For hydrophobic test, what we did, again, simple test, instead of measuring the contact angle and a lot of complexity, is that we just drop with some syringe, some water droplets in the surface of the concrete, and then measure the diameter. The wider the diameter of the droplet, the more basically hydrophilic, like so. And then if the droplet remains droplet, it means that it is basically hydrophobic. It doesn't like the water. So that might be important in some situation that you don't want, if there is any crack in the system, you don't want any fluid or anything go inside. The system actually repels. Then we did a shrinkage test with the blue plot. So pretty much at all temperature that we measured, the shrinkage of the system was around 50% lower than compared to the control sample, which is good for durability and no cracking. And this is some plus some theoretical studies that we did. What is happening actually in this compared to the control sample is that the red one, which is controlled in this plot, let's say if you get the stress strain, at some point yields and it fails. Whereas in the composite sample, the blue plot, even after some initial failure, the system still has room to grow, and there is a stiffening phenomenon that's happening, and that leads to better mechanical response and thermal response under different stress conditions. Then we did some adhesion tests after heat treatment. So imagine like geothermal, that you are exposed to some heat, and then the question is that what is adhesion to the steel casing or to the rock formation after this heat? So for that, we use a simple adhesion, like normal force adhesion test. I know there are like shear bonding and all this discussion that's important, but this just as a proxy, we use normal adhesion to the steel or rock. So there is a dolly that we connect to the sample, and then with like digital device, you push it, it pops up, and then you measure the normal strength. So we got, compared to the control sample, the normal like vertical adhesion strength was like 200 PSI. And then in our mix, it was almost twice, 400 PSI. And that was after 2 hours of heat treatment at 150 degrees. Then we expose this system after this heat treatment to some gas, basically to measure gas if there is any leakage or if there is any porosity, somehow we are missing it. So we created these cylinders and we connected to our this kind of parametric, this device setup in the lab we had based on pressure gauges and a very accurate flowmeter. So these systems, if they are failed or if there is a porosity, when we send the gas, CO2 or any other gas, there might be leakage, so we can measure the leakage afterwards. And if there is nothing, so it means that the cement has remained intact after the extreme conditions, which in that case, we didn't find any leakage. Then we did some abrasion testing. This is actually a good video. This is, again, this abrasion maybe not so much critical for the well cement, but you may argue that there might be a situation that abrasion may correlate to erosions when you have extreme condition. So what happens is that if the formula for abrasion is that the mass loss, you look at, let's say, 1,000 cycle with 1 kilogram load on it based on a standard. And then you measure the mass loss before and after, the lower the better. It means that there is no abrasion or erosion in the system. So we got here in terms of control, some of them actually broke at the middle of the test, whereas the samples C and D, which was the one that we optimized based on class H cement, there was extremely lower mass loss, so perhaps around 500% or more. So right now what we are doing is actually scaling up the system. The system extremely, we have managed and optimized it, so extremely easy. So it's all wet chemistry. All we have is like in the lab is like a 100-gallon mixing vat. It has the motor on the top. So we put these additives inside the system. And after a few hours, we get this right mix that is compatible with the well cement. And we can either send it out as buckets, as a liquid additives, or it could be as a dry additives to be mixed and then work with it as a dry. Dry might be perhaps easier because the weight is lower and shipment cost might be lower. But I'll be happy to discuss with you if you're interested in this. So here's actually the summary of my talk. I don't want to go through it, but basically created a multifunctional well cement based on class H that exhibit multiple properties as shown in this slide. Thank you for your attention, and I'll be happy to answer any question. By the way, the work was supported by the Department of Energy through a grant we got a few years ago. Thanks so much.
I'm Raphael with Megafec. Interesting presentation. The one thing I didn't see in your research and development is, have you looked into the lubricity that boron nitride imparts? Have you looked into how to improve rheological properties of slurries or free flow of cement in bulk?
Lubricity, this is actually an interesting question. So, this boron nitride itself is called solid lubricant. In fact, the most use of it in the commercial market is for the cosmetic industry. We have actually talking to some, the Chanel or Louis Vuitton, some of these big cosmetic companies are right now buying this because it is solid lubricant for like powders and other things, not so much in the material that we are developing. But we did some testing of this, rheology and pumpability. So we got this better rheology, like 65% lower yield stress and 40% lower plastic viscosity. So it is actually, because these materials slide over each other, they're called solid lubricant. So we did at a small lab scale this way. And I don't know what you mean by bulk rheology test. So. Oh, I see. Yeah, this is just pumping. I mean, this is like what we are trying to do is like a pumping of it in a larger quantity. Yes, this is possible. We haven't done it exactly, but based on this lab result, yes, we're expecting that it will be less energy needed for the rheology of it, to move it around. Yeah. Yes.
Question and comment. Your thermal K, what were the units? You're showing conventional cement has 26.8. 26.8 what watts. The standard nomenclature is watts per meter degree Kelvin, and I know conventional cement's closer to 1.
I'm showing a percentage of the improvement compared to the control, like this slide.
Okay.
20%.
So it's 32% improvement
compared to the Class H cement. Yes.
Okay, so it's like 1.32 instead of 1.
Right.
Okay. Okay.
I mean, if I add I can increase it further. It depends on somebody in the wants further. But the thing is that some other properties may decrease.
Oh,
so
yeah,
we are trying to balance everything.
Oh yeah, I totally get what you're talking about. There's a sweet spot.
Yeah.
The other question is, so it's a dry additive. Would that be 1% by weight of the dry blend of cement? Then is that the loading level you're
It's
talking
lower
about?
than that. Lower than that.
Lower. Yeah, that's what
Lower
I
than
was
1%.
thinking.
Yeah.
So I would just, a comment is it may be not good to put it in a dry blend, because what if you lose that minute amount as it's being boxed around versus if you use a liquid?
Yes, that's a good, valid point. That's why I'm towards the end, I showed this kind of liquid kind of as in a bucket to show it as a, additive. So that's easier than you.
Totally get that. Yeah. Thank you.
And just to clarify, your control slurry was like a 16.4 pounds per gallon Class H, cement, right?
Yeah. So basically, in summary, maybe the takeaway message is that we are changing the microstructure of the Class H cement to make it a better integrated, more connected nanostructure and microstructure. So this additive is helping as a template so that like a semi-epitaxial growth happens, crystal forms in a better way. Yeah.
Any more questions? Oh, got one. Oh.
Thank you.
Get something really better. So what does this additive do to the actual microstructure? What is your thought on that?
Yeah, we have actually done XRD, NMR, and FTIR. I didn't show it here, but when you look at the XRD, the peaks that corresponds to the hydrated product, for example, CSH, calcium silicohydrate, zonotolite, or tobermorite, the peaks are sharper and well pronounced. So we are getting better crystals and better formations of this. And NMR studies also show more connectivity. Like when you look at the SI NMR, more chain in the microstructure. Yeah, longer chain and longer connectivity. Yeah.
Any more? Oh, they're online. So we got a few questions online. Sure. So I will read them all for you. So from Mr. Simon, how was the Young's modulus impacted by the addition of your boron nitride nanoparticles?
Not much. Young module is not much impacted. So that's why I didn't report it. Pretty much around the same.
So the mechanical properties on like the Pessons and the Young's modulus are pretty much consistent with what Class H performance would be.
But as you know, Young module is the slope of the stress strength. So the slope didn't change, but the ultimate point at failure is that is increasing.
Okay.
Yeah.
Second question, economic study. What's the additional cost percentage-wise compared to a typical cement job?
So what we are shooting is just stay within the cost of one additive that industry is willing to pay. So the willingness to pay is, and instead of adding multiple additives to serve a function, we are just trying to make the cost comparable only to one additive which is within the range. So I can maybe comment on it later, but basically very low and within something that is already one additive industry is willing and able to afford.
And we have a question in the back here. Go ahead, sir.
Yeah, just a quick question. Is the biggest cost factor the cost of the boron?
Yeah, the cost of it, but we are also making it compatible with the cement. So there is functionalization going on and also the feedstock itself, maybe both.
Understand. Thank you.
Thank you.
We got a question over here.
I might have missed something, but is the boron nitrate, is that naturally occurring or do you make that?
No, it is a synthetic material. It doesn't exist naturally.
Yeah,
We need to make it, yeah.
Takes quite a bit of energy, doesn't it?
Yes, but compared to, I mean, this is not so much a scale up yet. These are nanomaterial. Yes, but since we are using very little amount of it, like less than 1%, so you can say that, it can be minimized. And also compared to other materials, say graphene and others, this is much more scalable and cheaper.
Thank you.
Right, thank you.
All right. Any more? Oh, we got one. Just came in. All right, here you go.
Just one interesting presentation. Just one short and quick question. Considering the molecular structure and solubility of these materials and the fact that they are very stable at the high temperature, has there been any study regarding possible environmental impact of using this material in large scale in subsurface?
Like leakage or what is?
I mean, just there, I mean, you might disperse them in the nature.
No, actually, the thing is that since they become like they act as a seed point, they become part of the crystal. They're locked inside the cement crystal at some point. So they don't leak out, or there is no leaching or anything. So, and also there's very little of it we are using. So not much environmental impact on the cement. So yeah, basically, yeah, they're locked and no leaching.
All right, any more questions? All right, very good. I got a quick question. What acid did you use for your corrosion pH adjustment?
It was, I think, carbonic acids or another one, but we used a couple. We looked at the pH, so we try to use acids that are pH 4 or 5, trying to
gotcha. All right.
control the pH with different acids.
So it's a good way to adjust the material that we talked about this morning. Materials maybe looked at for geothermal wells. So very good presentation. Thank you very much.
Thank you.
All righty.